Thanks. Okay, so broadly speaking, what we're trying to do today is give you a sense of what comes out of the camera. A lot of you might already know that. And a series of examples to show you how we tend to think about the data. So it's not going to be an exhaustive list of every single algorithm to process event-based data, more like a series of examples to show you how we tend to think about it, how we approach different problems, and really ultimately give you a bit of a toolbox of ideas and concrete algorithms to implement different things. And part of the reason why we are doing a presentation with multiple of us is that we all have favorite tools, favorite hammers, and when you have a hammer, everything looks like a nail, right? So really, the idea is to try and give you a bit of a more diverse example, because we do agree on a lot of things, but there are also some aspects on which we disagree. So on that topic, broadly speaking, at least our goal, and I think the goal of a lot of people in the community, is to ultimately have a real end-to-end neuromorphic system. That's the long-term dream, right? From the neuromorphic sensor all the way to the computer and perhaps even your motor control, everything spikes, no timestamps, just analog pulses throughout the system. The thing is, this is really hard to build. So what people have done, and really that decision probably dates back to AER, so that's not exactly recent, decades ago. The idea is say, okay, I'm going to have my neuromorphic sensor, it's generating some sort of analog spike, and I'm going to somehow convert that to a more digital representation, where I'm going to represent my spike as an address and a timestamp. And particularly in the case of a camera, you can then convert that into USB packets, and then do something else with those packets, feasibly send them to another neuromorphic accelerator, or perhaps even send them to a conventional computer. And a lot of the things we're going to talk about today are the sort of algorithms we implement on those conventional computers. And we do that for two reasons. One of them is as a means to build or invent, create new algorithms that we could ultimately put back to neuromorphic computers when they become a thing. And partly as a baseline, as a reference for those algorithms to get a sense of how efficient a conventional computer could be. If you create a neuromorphic computer and it's slower and more power hungry than the equivalent running on the CPU, clearly we're doing something wrong. The last thing that they could be useful for, shorter term perhaps, is for applications. If you can today take a neuromorphic camera, a conventional CPU, and build something that is better than its conventional counterpart, that's arguably very useful if you can quite yet end-to-end neuromorphic system. Okay, so let's first talk briefly about what comes out of an even camera as a refresher, perhaps. So this is side-by-side comparison of a very conventional camera, my smartphone, and a neuromorphic sensor, in this case, a Prophecy Gen 4, which only detects changes in luminance, which we represent here with yellow to mean that the luminance detected by a pixel went up, blue to mean that it went down. What's kind of interesting is that we certainly lose some of the information, in particular color, but we can see more things. You may have seen those blue streaks, those are raindrops that the conventional sensor cannot pick up at all. So the point is that if you know what you're trying to do with a sensor, say for instance, tracking cars, all this color information is wasteful. You don't actually need it. So having a sensor that throws it away early is perhaps a good way to reduce the load on your computation system.
Can you talk a little bit about the trailing of information of the cars? Because it seems like it starts to have to do with some lag in.
Yes, so here I'm using exponential decays, so inspired by the membrane potential of a leaky neuron, perhaps, mostly so that we can see the raindrops if you keep it to the tiny window.
Why are the raindrops only blue?
Probably because the off thresholds are, well, two reasons really. One of them is that actually they are yellow at the tip and blue at the trail. And because I'm leaving the trail, replacing it with yellow or blue. And also there's probably a fair bit of imbalance in terms of sensitivity between these types of units.
I would imagine shadows play a huge sort of issue in. So I was thinking that those cars, the trailing thing was the shadow. I guess it's not.
So yes, you do. And so yeah, each car is sort of doubled because you have the car itself and its shadow.
Yeah.
So you're right that it might be harder to disambiguate than with the regular sensor. That said, something that I find quite striking that the sensor is doing quite for free. If you look at the color of the car, it actually changes, right? When it's in the shadow of the building and in the light. And with a conventional computer vision system, you would somehow add extra logic to be resilient to that, whereas the even camera takes care of that for us by just calculating related changes. So another way to look at the same data, and that's something that Toby has done. I'm sorry, this is. Go to the next slide. There we go. Okay, is by adding time as a third dimension. And I think that that really shows the high redundancy that you get from a conventional camera, where you're showing the same data over and over again if the background is not moving. But the even data is far sparser, and we can feasibly extract useful information from that point cloud. That does, however, raise a question in terms of how we process this data, because clearly a system designed to load this stack of information may not fare all that well if you give it this very sparse point cloud. In terms of what the computer actually sees, in the case of a conventional machine, an image is really just a bunch of numbers, right? Each number represents the luminance in field of that pixel. For an even camera, what comes out of the system is essentially this table that keeps going. And each item is going to be an event with a timestamp, usually in microseconds, the position of the sensor and the polarity being whether the light went up or down. In a sense, the polarity plays the role of the luminance in the conventional sensor. What we have to do, however, because it's fast, is explicitly specify the time and position. In a conventional camera, this is sort of implicit. You're just getting a stream of those numbers, and you just know that whenever you reach, say, 1 million numbers, that's one frame, and you know exactly when the frames happen because you can plot the frame rate. So you don't have to encode those numbers. So that adds a little bit of overhead, but that's also part of the benefits of your own cameras, that you can have this fast representation.
So P represents whether an event is happening or not.
Sorry?
What does P represent?
Oh, so P is the polarity. That would be the color, blue or yellow. 1 for light went up, 0 for light went down. Okay, so that raises an important question, which is that what do we do with those numbers? How do we do something useful with this table? And what sort of computational model do we use on a CPU to do that in a somewhat efficient way? So if we look a little bit at the history of software frameworks, arguably the most reasonable pick would be to look at event-based programming. That's not exactly new, started in the 90s. And the idea is that your whole software ecosystem is designed to process events. Great, we have an event camera. Can we use that? So all those frameworks sort of conflate the notion of event and that of a function call. So whenever there's an event, that could be a user clicking on a button, that could be a web request, or that could be a camera generating information, I'm going to call a function. And what I do in that function is up to me. I can update the state of my system. I can dispatch new events to trigger other parts of my system and so on. There is, however, an issue when it comes to using those frameworks, a lot of them designed for the web or for user interfaces, for even cameras, and that has to do with the throughput. If you look at Twitter, or at least what they had a few years ago, worldwide, they were generating 6,000 tweets per second, which is quite a lot when you think about it. And each tweet goes to a computer, which responds to that new event by adding it to a database, sharing it with other users, and so on. But that is absolutely dwarfed by the sort of data rate you can get from a neuromorphic system. As a result, that impacts the sort of decisions that people make when they design those frameworks. With Twitter, they had like a massive supercomputer to process that sort of data, and thus they can afford quite a lot of overhead per event. It's okay if you have dynamic dispatch of different functions. It perhaps, depending on what that event is, you change the sort of function chain that event might trigger. We can't afford to do that with neuromorphic sensors. You cannot afford to change the sort of function pointer that you'll call whenever you get an event. So that's really the downside. Beyond 10,000 events per second, those frameworks really start to struggle. Something that is much better from a performance perspective are all the computer vision algorithms. And deep down, they all come down to linear algebra. The idea is that this big table of numbers looks very much like a matrix. And we like matrices. We're really good at matrices. In no short part, thanks to BLAS, which is one of the first linear algebra libraries, people have long optimized matrix multiplication, basically. And really the reason why things like MATLAB or Python are fast is because under the hood, they are using those tools to do the heavy lifting. And really when you're, sorry, when you are writing a computer vision pipeline in Python, you are gluing together with this high-level language, low-level operations that are implemented in those frameworks. And finally, so yeah, the downside is that this requires a matrix. So somehow you need to convert back your lovely sparse even clad into those dense frames. One of the downsides is that you typically need to accumulate your events for a little while, so that tends to increase the latency. Though we'll see that's not always the case. And makes it arguably harder to convert that algorithm to a spiking neural net. So if our goal is not just to build an application today, but also to think of the future neuromorphic computer and somehow convert those ideas into the spiking nets, this might be quite hard to do if your whole algorithm is operating on dense frames. Which brings us to the last category of software frameworks that you can use to process data from even cameras. And all those frameworks were designed mostly, if not only by the neuromorphic community, very clearly with even cameras in mind. And they all come down to even buffer processing. So the idea is that since the camera is giving you a buffer of events coming from the USB cable, the framework is going to help you iterate over those events quickly and operate on them. Some of those frameworks are actually hiding the fact that they're iterating on the buffer for you, and they make it look like you're doing event-based programming, but really you're iterating on the buffer of events. The biggest con, I would say, is that those frameworks have much smaller communities than those two, which means fewer resources, sometimes harder to get started, and so on.
Can I ask a question? Can you go back to the table which you had the?
This one?
Yeah. So what's a buffer here?
Oh, so a buffer would be the chunk of data that comes in one go from your USB connection. USB is roughly like TCP, where each packet has a header. So you typically need to transfer a lot of events all in one go, depending on the USB version, up to 500 bytes or something. So you get those little atoms.
A table of this stuff which is encoded in that USB
Yes.
packet?
So the USB packet would have, say, a few hundred to a few thousand of those events contained in it. So from a software perspective, what you get is one packet at a time. It's up to you to decide what you do with that packet when it arrives. Which is why it's not truly event-driven in the sense that every single event is going to trigger something. It's more that a buffer of a set number of those events is going to trigger a code.
And then how do you decide the criteria to make the buffer? Is it batteries?
That's typically decided by the camera. And often the cameras have two rules. One of them is that they will try to make buffers that are as large as possible because the overhead of the address goes down as the size of the buffer increases. But they also typically try to put a cap on the maximum latency you can expect. If you have a very low event rate, say 1 event per second, very unsensitive biases, for instance, it might take a while to get 500 events. So most cameras will send under full buffers after a set amount of time if they couldn't manage to fill it.
In general, can you assume that everything arrives in order?
In terms of time, yes, you can assume that the time is always monotonic. In some cases, time can repeat. So you can have two events that have the same timestamp, even in microseconds. Actually, if you have more than 1 million events per second, you guarantee that at least two of them have the same timestamp. However, in terms of X and Y, that can be completely sparse. So always the case, in particular with recent cameras, they tend to leverage the fact that they read rows one at a time and try to give you little vectors, as they call them, of several events that have the same X and subsequent Ys. But in general, especially if you have a low event rate, those two are quasi-random. So is the polarity. And that actually brings all sorts of interesting considerations to compression. For instance, if you're going to compress this information, you can be smart about how you relatively encode each row, since you know something quite important about what's in the rows. Gregor.
So if I stick on this slide for a bit, so decades of computer vision essentially has given us like lots of exploration with this kind of like middle column, this like frame-based approach. And so hence it was also natural for the event-based community to start using these tools and to do vision processing with event cameras. So arguably there's like lots of frameworks that have emerged over the past years in this like that are based on this conventional stack and also conventional input representation, which is the frames. Now, with event-based cameras, we have now a sensor that reacts to the scene. The data is completely different. And you get this 3D point cloud that sometimes is maybe sometimes very dense and sometimes very sparse, depending on whether you shake this thing or where you point it on your just static garage door or whatever. So it gives us also now different means how we work with or how we represent these events that we adapt depending on the hardware that we have available, the algorithms and such. So I would say that the classical one obviously is the 2D frame. Here we just bin a certain number of events that can be over time, that can be a fixed number of events to just create a short snapshot of what we see. Now, if we bin a frame by time, but really there was no movement in the scene, we just get an empty frame. So we'll come back to that a bit later, how that can also create problems. Some other representations that we can use with event-based data are really treating all the events that come out of the camera event by event. And it comes a bit back to what Alex said earlier with the frameworks. On conventional systems, this can create huge overheads. If you have to call a function for 1 million or 10 million events per second, this will likely not be working in real time, or it will not be efficient, let's say. We have some spatial, temporal, locally representations. So one example of this would be a time surface. So here you look. You receive an event and you look into its spatial and also temporal neighborhood, and you create a descriptor that kind of encodes, for example, time in a kind of like heat map, so that you can get a sense of the history of events that you received in its neighborhood. So this is arguably somewhat inspired by the retina. It keeps like a history, or like that has a spatial contrast. It is a spatial contrast sensor, and that also knows like some of the history of activation that actually occurred at that very pixel or neuron. And another one, so we talked about 2D frames, and another representation that we can look at is really 3D volumes. So here we look at a complete. It doesn't have to be like voxels, but like 3D voxels, but it can literally be a 3D point cloud. And we're also going to look at some algorithms where we can exploit that, namely complex maximization.
So in the time surface,
Yes.
why is there no noise? If you figure it out,
Where is there no
noise event?
noise? Yeah. So this here. Okay. So what is this actually? So we have here. Imagine the sensor being like this on the focal plane on X and Y, and we receive now a latest event, and we keep actually a memory of all the events received. We keep the timings of all the events received for each pixel. So here it's smoothed out, but really, let's say this is maybe an event, a pixel array of 3 by 3, let's say, okay? or maybe 9x9 or something like that. And so you generate then, when you receive this latest event, you will decay based on the decay on the time of each event that you received in the neighborhood. You will just form one 9x9 or whatever your surface size, one descriptor, one image patch that encodes now all the history of the neighboring events around it. Is that
So you do some spatial computation.
so this is using spatial, because I look at the events that are in the spatial neighborhood, but also I also encode the notion of how far in the past have the events occurred in the neighborhood. So also a temporal context.
Yeah, that's a correct, right?
Yeah, exactly.
Yeah, so if there is a noise event,
If there's a noise event, exactly, then this is actually, so this is very sensitive to noise. So this is yeah.
Also, does this assume that each pixel can only be activated once?
So this is, I mean, here in this case, you would create one of such descriptors for each event. So yes, one surface per event.
But I just in its first implementation, yes, they would typically assume that you just use the most recent pixel from your neighbors, sorry, most recent event from neighbors. There are iterations on those ideas where they try to account for a larger number of events, build a 3D version of that in some sense. It sort of becomes a 3D volume, a 3D section of that larger volume.
Yes, the pixels, they are still integrating light over a period of time, right?
Not really.
Okay.
So the analog circuit inside the each pixel detects changes directly in luminance on the analog signal. That said, since the photodiode is a low-pass filter, one could argue that since pretty much every low-pass filter is an integrator in some sense, you still have some of those effects. So if something moves incredibly quickly, the photodiode may not be fast enough to follow that
So
effect.
what are those practical limits in current systems?
That really depends on the sensor generation, and we're still, I think, as a community working on properly assessing a lot of those things, especially with more recent commercial sensors for which we don't know the circuits. And sadly, the sensors are really efficient and give really good results, so it's very tempting to use them nonetheless. I think that the low light performance is getting good, as in we can use it for stars and so on. But I don't know how that translates to lux per pixel, for instance.
But just trying to understand what causes the signal and what are the bounds in sort of various domains. Obviously, we want to operate in some nice space, but we want to know the edges of that.
Yes, and I think that touches on some of the bio-inspired algorithms as well, in that a lot of biological systems tend to operate with very high levels of noise, whereas human engineers like to get rid of the noise as soon as possible. So there are all sorts of interesting ways of looking at those trade-offs.
All the cameras which I saw, even though they were relatively stable, there's a lot of jitter kind of in the
Yes.
image. So, and on the other hand, your processed images, they're not there. So just trying to understand what processing goes on when and so.
I see.
Maybe it's worth wondering, this is just a quick overview of how you can work with this. Time service is not the only example of things you can do. I think we're just trying to show that you want different kinds of context in different situations, right? So like Alex said, the spatial tempo locally represented time service is kind of a 3D volume, just very local, right? So I think that's one way to see it. You can go from the point representation and then you blow up onto 3D. Of course, when you get to the full 3D volume on a full recording, that's not real time, right? So that's also something to keep in mind. If you want to think about, 5 seconds of data, of course, that's not gonna work if you have a real time constraint. But maybe as we move on.
Is that okay?
Yeah, sure.
Let's talk about power consumption a bit. So if we look at like a pipeline of processing event-based data, so we so let's not get hung up too much on the exact numbers, but the idea here is that we have an order of magnitude roughly in between these three stages. So we have first one is really on the pixel array itself. Now here it doesn't make much difference whether this is an event-based sensor or a conventional sensor. Then we have for example, the CPU or a USB chip or like maybe a low power FPGA that tries to get the data essentially out of the camera and reroutes it. Okay. And in this case, if we look also at processing data on a GPU, now this here is roughly this would be an embedded on the lower end of a wattage of a GPU. But what we want to show here is that just replacing, if you have such a computer vision pipeline and you just replace your conventional sensor with an event camera sensor, you're not by all of a sudden going to minimize the power consumption by a lot. You do need to optimize the whole pipeline because in neuromorphic engineering we often talk about the power efficiency of the pilot systems, and so just relying on the sensor for you to do low power computation is not enough. Now there are some other properties of the event cameras that we might want to exploit, and that might justify for us just simply switching the sensor, namely the high dynamic range. So the event cameras are very good at recording both very bright and very dark events or scenes or at the same time, and the high temporal resolution. So we go down to microseconds, tens of microseconds of temporal resolutions for of the time stamping of events. And that means if we record very high speed motion, unless we shake the camera or something, or just the whole focal plane or the whole scene is moving, we can record single objects with very fine-grained temporal resolution. So that might justify replacing a high frame rate camera in that case, because in this case we can really use some of these properties that are specific to the event camera. Alex, do you want to add something to this? Or?
And I think that you covered it.
Crucial, this is something that's really, I think, is absolutely crucial when working with event-based camera. Now, in the sense, when you work with conventional cameras, it doesn't depend, the amount of data that you get doesn't depend on the scene. But now we're working with a motion detector essentially, and so you have to rethink your pipeline depending on what you record and how you record it, right? So on the left-hand side, this is one of Alex's recording of stars. This is, you barely, you can see a little dot here moving, but essentially most of the background is just black, right? You're pointing it into deep space. This is all, this is in real time, counting down the seconds, and you will only receive some bits of data for these small stars that you record. This is very different, and the amount of data that you get and how you perceive it is very different from a self-driving scenario where you actually get relatively dense input because you are moving yourself, right? So there is really a trade-off in terms of, so here we have a stereo vision system of event cameras. Down here is conventional cameras, and these are some disparity maps. But what my point here is that you cannot apply the same algorithm. You can, but it will not be efficient to the left-hand recording and the right-hand recording, right? So you really have to let the data speak. So this is really, if there's one thing that you take away from this talk, or at least from what the slides that I present, I think it's let the data speak. Really, you plot it and visualize it, and based on that you will choose the algorithm.
What is the third column in that thing? Can you explain a little?
Yeah, so this is because this is a stereo vision system. So you have two cameras mounted on a car.
Yeah.
And then you can, from that, you can calculate a depth field. This is ground truth for depth, for a depth. So how far are things away? Okay, so based on that, now we said, okay, let the data speak. So there's several different algorithms that we might apply to event-based data. This goes from relatively simple ones where we use, some neuromorphic inspiration of maybe some biologically inspired neurons to work with the events directly, one by one. Alex is going to talk a bit about that. Contrast maximization, this works on 3D volumes. This works very well in the case of like the star recordings, for example. Yeah, we have like optical flow, we have more conventional ANNs. I'm going to talk a bit about that, if we just create frames, what we can do with that and process on GPUs. Coincidence detection is an interesting one where this is, I would say, really biologically inspired. We use, for example, the high temporal resolution, and we now all of a sudden work with delays of events between pixels. So I think this is quite an interesting one. Time surfaces we already looked into or saw a bit. We have the spiking neural networks that as well try to process the data now event by event, but try to apply more complex machine learning algorithms to it and some 3D operations. Okay, let's start. Okay, starting here with the ANN. So this is from papers from CVPR. So like computer vision conferences with a long tradition, a long history. And so what people do here is they kind of split it up into two parts. So here we look at the architecture for object detection, which is a relatively complex task, right? This is not just counting events. So here you really need to have like a very complex network and complex optimization scheme to do that. And how people do that is you split it into a spatial feature extractor part in the beginning and some kind of temporal feature aggregation at the end. Maybe I should also say that the events here that you work with are a form of either 2D frames or, well, it's a form of 2D frames, but you will need to guarantee that this generates enough signal. So you will typically accumulate over like 50, 100 milliseconds of time to really guarantee that you can see something in the scene. That's for the event input. So then we do spatial feature extractors. This is a stateless part of the neural network, right? So here you have your CNN, or in the case of work from NeurOps from 2020, or we can, nowadays use a vision transformer at this part to extract the spatial features. And then, because if you think about the self-driving scene, for example, and you're moving, and so you're generating a lot of events, but then you're catching up, you're moving at the same speed as the car in front of you. So the relative speed is 0. So this car might not generate many events anymore. So then you need to have some kind of temporal feature aggregation to still remember, hey, this car is still there, right? So that's because the event camera is a motion detector and only records changes. We need to have some kind of aggregation here in the model as well that remembers where things were in this case. And then, yeah, we can, these are some exemplary outputs where you can detect cars and pedestrians and whatnot. But this is a bit to give you an example of how classical computer vision pipelines are adapted. So normally, probably, it would probably stop here, but then we can add this kind of temporal feature aggregation. This can be your LSTM or this can also be spiking. So in this case, none of this is spiking, right? So we're working with fully floating point values. Here the authors were not interested in making this, adapting this for spiking for neuromorphic hardware. But maybe we could think of other variations of this where this kind of memory types here blocks is spiking neural network, and yeah. So this is the stateful part. I think this is it for. Yes.
In one sentence, so this is classical computer vision,
Yeah.
But you replace the input of intensity by a derivative of intensity.
Yeah, exactly. Yeah, I mean, so but sums you still sum over time. So it's not just the derivative of intensity. Yes, that's the events. But in order to generate enough signal, you still need to aggregate those over time.
But you do the same in frame base, you also accumulate over frame base.
True.
I'm assuming they are creating this 2D image, right, when they're feeding to the network, correct?
Yes. Yep.
So how do they choose this window size? How large or small it should be? Because I'm assuming this is user-defined parameter, right?
How large is the window size? You mean the you're talking about the temporal window size?
Yeah, temporal window size to convert into.
Yeah, that's a good question. So if you choose your temporal window too large, you will the lines, like, it will basically blur your input. So the window size is really dependent on the speed of events that come in, or the speed at which you're moving, for example, in the case of automotive detection. So that's really important factor. Again, looking at the data, like it makes a difference whether you record high speed things, or in this case, if you're moving with high speed or relatively low speed. With that, you will choose your temporal window. So basically,
No, I understand, because the scene is dynamic, right? Sometimes
Yes.
it will be slow, sometimes it will be fast. And then if you fix it, so sometimes it's blurry, sometimes you miss the event.
Sorry, can I suggest we move on, because we have a lot more algorithm to cover? Maybe afterwards we can break out and we have some tutorials where we can go into more depth of each approaches. Would it make sense to then address detailed questions there?
Yeah, sorry.
They're great questions though, they're great questions.
We're a bit short on time, I think.
Is it color right?
Okay, briefly, so here the goal we set for ourselves was to see if we could build a self-playing pinball machine. So there's a neuromorphic camera on top there. And with a conventional camera, what you would probably want to do is process each frame, identify the ball with some sort of circle detector, build a tracker, and so on. We did something quite different, which is really just have two receptor fields near the pedals. And we're just using what is really just a CPU implementation of a leaky integrated fire neuron. Whenever you get a spike in one of those little rectangles, add one to a counter, exponentially decay that counter. And if you reach some threshold, you spike. In this case, spiking means activate the paddle to just skip. Turns out that, especially if you're playing with three balls, which is hard for humans, you get performance about on par with a human being if you do this very simple thing with just two neurons. So I think that it speaks to the simplicity you can reach when you have those really high-speed sensors, and sort of look at problems the way insects solve them. So they're not trying to be particularly smart. They rarely predict the future. They just have incredibly fast response speeds and very simple local algorithms to solve the task that they need to solve to typically survive. Jens, should I perhaps briefly
mention it for sure?
Let's mention it. Okay, so contrast maximization looks at the data in a completely different way. We're looking at a 3D volume instead. So if I do that with stars, for instance, so that's the recording we saw earlier, with those very faint dots moving in one direction of the satellite in the other, I can feasibly represent that entire point cloud as a 3D plot that we did earlier. And the idea of those algorithms really is to try and manipulate that 3D volume almost as a geometric thing to try and extract the information I want. So contrast maximization, technically it's a shear operation. Here I'm doing rotation, but that's close enough. Consists in saying, okay, I'm going to rotate the thing until I get a good alignment. And when I do, that tells me what the speed of all those objects is, and I can also use the clustering algorithm to find them. That's how we build star maps, for instance.
Is it clear that this is XYT
yes,
representation?
I should mention that. I can also rotate in a different direction here, for instance, and I get 3 different dots. Those are 3 satellites that are moving in a different direction.
How is it different from optical flow?
The biggest difference is that this is far more global. So it's not as efficient as optical flow. You need to integrate for quite a lot. But if your object breaks down, optical flow really struggles if you have 3 points that are really far away in space and time, whereas this would work quite well in this scenario.
Maybe this is just a trick, right? We try to find the parameters so that we can align, and it has been applied in the literature, both to flow, both to global alignment.
Mm-hmm.
You want the next one?
Yes, the next slide. No, sorry. I just wanted to briefly show. Oh no, it's stuck. Sorry. To go back to the presentation.
In your pinball case, what you're defining as a neuron is just a counter that fires at a certain value? Is that
Yes, it's very much a program thing, so it's not actually a neuron in any meaningful way. That said, it should be relatively easy to port that to more neuromorphic hardware. Brief other example where contrast maximization does work quite as well. Just wanted to show off a little bit. So yesterday we went to the end of the valley to try and record the jets that flew overhead. The recording is not terribly exciting, as you'll see. We have like this little dot here. It's one of the jets. The other one will be right after it here. And we also have a bunch of insects flying in the field of view here. And if we look at that in 3D, we get a lot of interesting information. So if you look at your data in 3D, you don't necessarily are not necessarily trying to find straight lines. You can also feasibly apply all sorts of interesting algorithms to really try and extract those straight lines or those complex volumes. So it's not always efficient, but quite often an interesting way to think about the data.
All right. Yeah, sorry for rushing on. There's so many things to cover, and I want to be sensitive to the fact that many of you would probably want to do different things, right? So contrast maximization might be relevant for some, ANNs for others. What I'll briefly talk about now are some of these algorithms, which I'm going to rush over really quickly. I think we talked about time services. The reason why I think that's a wonderful example is because it's Byron-Spire, of course, but it works really, really well for detecting features in space-time, right? That's a reasonable thing you want to do. And so you can imagine you can put these in different layers and work on the hierarchies of these different filters. That's excellent work from Gregor et al. In 18. And so one argument I want to mention is that we've extended that to work with then spatial temporal time surface called the receptive fields, where we are then moving into the spiking neural network domain. So you can think about it as a continuum where you're basically trying to squish frames in time. That's the ANN approach, where you need a lot of time, a lot of context before you have enough signal to meaningfully work with it. We can also imagine taking some of that state, that context, and imbue it into the network. And that's essentially what integrators are doing, what our neurons are doing. And so some kind of network architecture, the specific architecture is not important. I just want to show you that this is a relatively simple layer-wise network where you can imagine putting in some different convolutions block, but with spiking temporal activations. And if you do that in a certain way, you can then get very nice invariance and covariance properties, not just to the temporal surfaces and the temporal features here, which are of course also spatial, but you can be sensitive to certain transformations, certain changes in your input. And there's a wonderful paper, I think in the 70s, something called "What the Frog Eyes Tell the Frog Brain," and that's exactly showing that the eye is actually not sending invariant signals; it's saying covariant or equivariant signals. I'm happy to elaborate that if you're interested, but I think it's a pretty cool thing. So we both have the spatial features and the temporal features. That's just the takeaway from this slide. But the reason why I think that's very, very nice is because people normally blame GPUs for not being neuromorphic. But I wanted to show you a brief example where you can take an event camera and then create frames that are very thin. So admittedly, we're still using frames. It's not neuromorphic, it's not individual events, but they're so thin, I would argue that we're close to real-time processing, right? So we're working at roughly 1 kilohertz. And if you send that to a DPU that then simulate these neuron dynamics, you can kind of imagine that you have a neuromorphic system, right? Because the temporal integration doesn't happen in the frame, mostly it happens in the network. And this is my colleague Juan, who's we're having 3 different cameras. You can see the output here very barely. We integrate all these cameras, and then we find the position of this hammer based on the event-based vision. So this is completely in real time. So the reason I'm showing you this is that if you want to work with real-time spiking networks, I think this is a very easily accessible approach. Is it neuromorphic? Well, maybe. Do we want better neuromorphic hardware? Yes, but at least this is one way to do it. So a final thing we just want to talk about is exactly then where you can run these things. So what do you then do? Because obviously it's not enough to think about the algorithm, we have to execute it. And if you're, for instance, Alex, and you have a camera in space, you can't just, you need to process that somehow, whether you do it on the sensor or close to the sensor in space, or whether you dump the data to recording and then process it afterwards. So all these factors matter. And we wish we had like a golden rule. If you have these conditions, you do these and these things. I think it's more flexible, like Gregor said, like let the data speak for you. But what we want to give you now is some overview. Please don't get into details with all we are glossing over a lot of problems here, but some overview of what could be hardware platforms relevant for your particular problem. So CPU, as you know, have few cores, but use a medium amount of power, you can say. That was the axis we had before in the power consumption. It's good for low complexity, and if you have all the time in the world, you can take one event at a time, look at it, and do something with it. But it will take you a while, like you said before, right? If you have 10 million events coming in per second, this is probably not something you want to do real time. DPUs have a very high throughput in the sense that you can take a vector of events or a frame of events, and you can work with it with singular instruction, multiple data architecture. So just have high parallel operations on your throughput data. Unfortunately, this is really power expensive, right? So you shouldn't put this in space. Of course, we're here because we care about neuromorphic systems, and neuromorphic hardware exists. This is the BrainScales 2 chips, like for the excellent graphics from the Heidelberg team. Right now, these systems have quite low throughput, at least compared to these ones. So it's still quite tricky to work with event cameras, especially if you have 1280 by 720 pixels. That's a lot of pixels, right? That's roughly 1 million pixels. So you need at least 1 million neurons that you can feed that into if you want one-to-one correspondence. They're very high in parallelism, obviously, but very low in power. So our hope is that it gives you a rough idea of where you want to be. I think for vision, I hope I'm not offending anyone to say that it's probably a bit of a way to go before we can do fully neuromorphic architectures. There are very interesting chips by Dylan, for instance, who is online, by Dylan, and Spinnaker 2 that are, you can say, borderline neuromorphic that work with digital representations and then can do these things. So SPEC is one example that actually integrates an event sensor on the chip. So you can directly program your CNN and dump it on chip, and they will just process whatever the sensor senses in this like integrated system. Yeah.
That low throughput though is not necessarily a permitting problem, right? Whereas the other things are really fundamental features. Or low throughput, which is something to figure out, or will it always be difficult to map one-to-one event sensor pixels to some neuron?
Yeah, I mean, that's what you ideally want to do, right? But it is, as Alex said, that's the holy grail. But it is, I mean, it will require you to physically wire the pixel to the physical neuron somewhere, right? And that can be a bit of a hassle. But yeah.
It all depends how you define neuromorphic, right? Because there's approaches that are almost GPU-like. We call it neuromorphic rather than GPU-like, but that can get
that's an
really
excellent
and extreme efficiency.
Yeah, that's an excellent and very confusing point. Yeah. So maybe again we should just talk about what applications you have. Come to us, talk to us, and we can figure out. That's a question.
Have you guys ever seen anything where people have like theory for something equivalent to a FIR filter, but in the event domain?
I think that that's a massive gap in our shared literature. We are lacking proper signal processing theories when it comes to events. There are a few, but nothing that yields. There are different ways of mathematically modeling this, but we don't have anything nowhere near as powerful as, say, the sampling theorem, for instance, that really lets you predict the performance of different systems under different conditions. Perhaps because we're not using the right mathematical framework, or perhaps it already exists, it's just that we haven't realized that it applies to our particular case.
I just bring that up because, so back when I first started using these, one of the most interesting things to me was that you could do something like a running mean. And it acted kind of like an FIR filter, but it was temporally adaptive. And that was really interesting the way it worked, but I'm just curious.
So yeah, that definitely works in this bubble, I would say.
There have been some attempts in the auditory.
Oh, interesting.
Yeah, and there's a lot of work in interpolation theory, because essentially this is not interpolation, right? In which interpolation, so you interpolate over time, you have discrete points.
My 5 cents on this particular aspect is that conventional signal processing really started with this idea that you'd reconstruct a signal. It was mostly about signal transfer. So the sort of natural heuristic to test different things was to say, how good am I at reconstructing the original signal? I would argue that with a neuromorphic system, what we're trying to do is build a robot that takes decisions. The robot isn't trying to reconstruct a perfect representation of the world. It's trying to get enough information they can make a meaningful decision. That, I think, dramatically changes what you're trying to get out of your signal theory.
There are also some work in level sampling. So time sampling, there are works in signal level sampling.
Yeah.
To find out electricity because it's nothing but level sampling. Right?
Yeah. That was actually the question I was going to ask. Do these pixels fire at different rates, if you will, if the intensity is increasing rapidly or something like that? Yeah. So that would relate to this level business that is.
Yes, but not like that. I think that we can take that outside and look at like how the pixel samples the signal.
Yeah.
Sort of, but not really.
Okay.
Is the short answer.
Okay, so focusing on events, they don't come at an equidistant time. So is there non-equidistant sampling theory involved in this processing?
There are, but they usually don't account for the fact that there's a strong correlation between when you sample and the signal itself. So there are theories that cover randomly sampled signals. They usually assume that you don't know anything about the signal, just have samples at random.
Okay.
Whereas here, it's not random. We sample precisely when the signal changes. And I think that we need to account for that in the theory for it to be as powerful as it can be.
But that's what the interpolation theory does.
Okay.
So and this is something that's used in polynomial, like Reed-Solomon codes reconstruction too. So where you find the smoothest polynomial that goes through all the even sort of points here.
I see. But then I'd argue that they're trying to reconstruct the original signal.
So it
Not
depends
so
on
much.
what is your cost function. So
Okay.
if you define your objective function the right way, you find the polynomial that goes through all the events that satisfy the criteria.
Okay.
Johannes, you have a point?
What Chetan was mentioning is it's exactly this level sampling theory. It's exactly that, like you sample a signal when it crosses a critical threshold. So you have non-uniform sampling at time, but you have samples wherever something specific happened in your signal. I think this is just that.
I think you're right. Does that yield powerful results that we can visibly use to predict performance of the system?
I don't know. The only thing I know is that people were looking at whether this is equally powerful as uniform sampling, and the answer is yes. And that's pretty much all I know. Maybe it's
That's already a pretty strong result, I'd say. I was not familiar with that.
So that's where interpolation is there. Lazar's work is related to that.
Lazar's time encoding.
Timing, yeah, it's interpolation.
Because in this case, perhaps I was wrong, and there are seeds for powerful theories, and maybe it's just a matter of bridging them or applying them to vision so that we can make informed statements about performance of filters, for instance.
We have one last slide.
We actually have 2 more slides. This is neuromorphic hardware. You can look at it afterwards. But what we want to show you is that we prepared some tutorials and demos. So I'm going to go through them now, but keep in mind which might be interesting and relevant for you, because then we have code and tutorials so you can get hands-on experience that you can come and talk to us afterwards. So one thing is just to start with a Davis camera and then configure and record data. So that's if you want to record fireworks or something else, this is a great place to start. Notice it has one green chili. That was Alex's idea of hotness. So this should be relatively accessible. You can also watch birds, right? So we saw that probably in the demo we had a few days ago, where you can look at the cable car and like see what data you have. So Toby has been working on a really cool demo for rock, paper, scissors recognition. And so this is also using one of their framework called, I think, FPAA, that uses like a conventional, I would say, image processing pipeline. Notice the two yellow peppers. That's not because it's you shouldn't think this is super hard. It's just a little more involved. You can also just stream frames in Python. That's a framework that I demonstrated with the spiking neural network. Just plug in a camera and then get them into PyTorch or JAX and work with them directly there. So that opens up all the machine learning accelerator platforms and GPU acceleration. Then Alex made some really cool tutorials on loading and processing event recording. So if you want to, for instance, detect sprites or lightning in space, you don't care about real-time streaming. You just have a huge chunk of data. You want to go through them in a meaningful way. Finally, we have a demo on how you can track, for instance, a laser pointer. This is a demo at Capocaccia we did last year. We have an event camera pointing at a wall, and then you can have a laser pointer, and then the camera will then move according to that laser pointer, because we can quickly iterate over the frames. So I hope this kind of covers the applications you have in mind. I hope you got. I think our goal was to give you hands-on, at least tools that you know, so you know what you can do when you're here in Telluride.
To confuse it with everything that's possible.
Yeah, sure. The diversity of approaches and ways of thinking about the data and thinking about the solutions. And I think our message is really that there are no wrong approaches. It's okay to use a GPU and frames if you have to make sense. It's also often elegant and useful to just think of your data as just individual events, try to build local descriptors.
Yeah, just to do the space.
It really comes down to what you're trying to do.
Great.
Thank you.
Thank you.
Yeah, I was just curious.
That's an offset.
Okay. Oh, okay, there you go. Okay, this is the outline of the full set, so I don't think I probably stop by half. So I will cover event-based vision, event-based convolution, and skip maybe all that is about membristors and so on, and maybe leave it for some other time later.
But you might ask the audience whether they want to, which part they want to hear about.
Okay, so you want
Can we go back to
event-based-
the other thing?
You want rather, who wants event-based vision and processing, sensing and processing? Okay, who prefers membristors? So I think that we leave membristor for some other time. Okay. I'd be around the full workshop, no? Starting today. Okay, I know everybody knows about this, but I always start with this frame-based vision, which is very compute intense. The sensor needs to take picture after picture, and then the computing system needs to process frame by frame. Also, it's very compute intense. However, our brain doesn't work like this, and there is a very so our brain doesn't take pictures, and our eyes don't take pictures, and our brain doesn't process picture after picture. No? So everything is done by events. So we have our biological retina that sends information encoding to the brain, and the brain, the visual cortex, will process event by event in general. And actually, there's a very interesting paper that I like a lot to use for introducing this subject by Simon Thorpe in 1996. It's pretty some time.
Yeah, but has it stood the test of time? Has this finding stood the test of time?
Yes, yes.
It has.
It's
I believe it
still-
stood the test of time.
It's still,
Okay.
yes, it's still.
Yeah, it has, right.
So he basically demonstrated that the information encoding for, at least for visual processing and consequently for all processing in the brain, is highly energy and information encoding efficient. And he does a very simple experiment. No, actually, when you go and visit him, he sits you in front of his computer and he tells you, okay, whenever he flashes pictures and he tells you, okay, whenever you see, I don't know, a human, you click the mouse, no? And he measures the delay between putting the picture on the screen and you hitting the mouse.
No, we don't want that.
And then
It's too loud.
they repeat, no? He does many trials and gets some statistics. And he knows about neuroscience. He knows where the spikes are going. So a picture is flashing, it stimulates the retina, then it follows all these paths. And you can see there are milliseconds, no? At each node in the V1 cortex, there are 40 to 60 millisecond delay since the flashing. In the next one, V4, for example, it's 60 to 80 milliseconds delay since the flashing. And more or less at the PFC, in the front lobe, is where the brain already discriminates whether there was a human or not, and then takes an action according to that recognition. And then goes the spikes go to the motor cortex control, which is on the top, MC. And at that point, there is a delay in the range of 140 to 190 milliseconds. And then a command is given to the muscle of your finger. No? And at the end, it takes about in the range of 200 milliseconds or so. And this he measures. No? This he measures, makes the statistics, and gets a nice, Gaussian curve and with your delay. Actually, he does this experiment also with monkeys. He trains monkeys to do that, and monkeys are faster. And why? Why do you think monkeys are faster? Slightly faster.
They're smaller.
They're smaller brain. Yeah, they have a smaller brain, so all these wires connecting the different regions of the brains, they are shorter, so the delays are smaller. So monkeys can react faster. And also insects are very, very fast, no? But this is for human. Okay, so this he measured. But then he also knew the technology. The technology is biology, the neurons, which are slow. Each neuron needs time to fire, to deliver a spike. And he knows how many layers of neurons are involved in this process. And the conclusion is that all the neurons, if there is a neuron involved in all this vision, recognition, detection, decision-making, and motor actuation, all these neurons, whatever neuron is involved in the process, that neuron only has time to spike once. There is no time to spike twice. So in all this complex process, the neurons that are involved, which are just a subset of the full brain, each of them only has time to spike one spike, and that's it. The one single spike.
But lots of neurons can spike.
Lots of neurons, yes, lots of neurons, and probably many other neurons that don't have any effect in the decision and everything else. But whoever is involved only has time to spike once. So the conclusion that he drew is that, okay, the information encoding in the brain is highly efficient, and it's worth to try to mimic. And also he postulated, I don't know if this is really true, but some truth is in there, that the energy consumption is related to the spikes that are communicated from one part of the brain to the other. Probably it's not completely true, but
it's about half.
Yeah, about half. Yeah. But it has an impact, no? So the brain tries to minimize that. So it's interesting to try to mimic that, and this is what address event representation is all about. Who does not know anything about address event representation? Everybody knows about it. You don't know? Okay, the idea is very simple. Whenever you have a chip or a pixel in a chip, and there is a neuron in that pixel, you code its address. And when that neuron sends a spike, it puts the address or some ID on a high-speed electronic bus, inter-chip bus, that only needs a few nanoseconds to communicate, but you can multiplex a lot of spikes in that high-speed bus. No? And that is how the high connectivity that we want to mimic in the brain, we time multiplex it through high-speed buses. And here we have a system where, for example, the first chip could be a retina that is sending out spikes. There is a fan out. It is sent to processing chips. And every time there is a spike, the retina puts the XY coordinate, also some other info also, like the bit sign or whatever. No, you you are free to add more information to each spike. But this is the idea. You just are sending spikes around, and these spikes are processed as they flow. There is, and at least in this approach right now, there is no timestamping. All the spikes flow as they appear and are produced by the different neurons or pieces in the chain. This is in at least the original concept of AER, address event representation, that was proposed in 1991 in Caltech. And time represents itself. Everything is data-driven, event-driven. Normally, the pieces in purple, they could be convolution chips, for example, that they collect events and generates events that represent the convolutions of what is flowing in and so on. And let me talk very quickly about the Caviar project. The Caviar project is something that Toby and I are very proud of.
And Chi also,
and
right?
Chi and Philip Hasler and other people and the people from the Sevilla University. So the Caviar project was in 2002, and I think it was probably the first one that we built a fairly complex multi-module system where everything was interconnected through AER buses. No? And this is actually the project in which Toby invented the DBS during this Caviar project. And here is a picture of the full system. No? You can see there are like 15 PCBs. You can see the picture down there. So each PCB is an AER board that receives AER events through some parallel bus. You can see the buses are these parallel hard disk connectors, old hard disk connectors. And everything was flowing in real time. There was no time stamping, there was no C code, nothing. No, everything was hardwired and implemented in real time. The first piece, number 3, is actually Toby's DBS retina. The boards in blue, these are like interfacing boards and monitoring boards. In the monitoring boards, we did time stamping. So they were collecting the events, putting timestamps, and sending the information to a computer so that we could visualize on a computer screen, we could visualize the events. Because the computer would take the time-stamped flow of events, build frames. So it would take like every 20 milliseconds, build a frame of all the time-stamped events and put them in real time on your screen so that we could see at the different nodes in the system, wherever there is an AER monitor PCB, this we could plug to the computer and see. Actually, on the left, you can see that we are observing 4 nodes in the system. The first one, top left, is the actual output of the retina. Below is the output of the convolutions, which is these 4 modules that we have labeled with 6. These are 4 convolution chips. They were just detecting the large circle. No? So we had a circular kernel to detect in real time the large circle rotating. By the way, the retina is down here. This is the retina, and it was observing a rotating disk with different figures. And the convolution chips, they were programmed to detect the large circle, the center of the large circle, and follow it. And then there was a winner-take-all to clean out the output of the convolution chip, which is you can see in the top right. You can see the computer screen in the top right. This is the output of the winner-take-all chip. No? It would give you like the clean trajectory, removing all the noise that was coming out of the convolution chips and so on. And then this trajectory was used to center the big circle in the center of the final output of the system, no? Because there was a closed loop tracking and centering scheme.
Do you guys get it? It was electronically foveating that big circle, electronically. Because you had the events and you could like steer the events so to keep the big circle foveated electronically, not mechanically. Right? It would discard all this stuff. Yeah, it was really cool system. Really worked at super high speed for this very restricted problem.
Yeah, at the beginning we tried to center with mirrors, not have some like a panel unit to center, but then we decided that we would do it electronically and simply operate on the coordinates. So the center, that was the trajectory, that was provided by the Winneticode chip was used to subtract the coordinate from the direct output of the retina. So everything was relative made to the center of the trajectory.
And everything was directly computed on FPGA logic circuits. Basically, there was no software anywhere in the system except to record everything. Everything was pure hardware logic circuits and mixed signal circuits. It's really quite a remarkable thing, I thought.
How fast was it spinning?
Maybe 50 hertz or something.
What you see, yeah,
It was pretty fast.
maybe 10 revolutions per second or so.
Okay.
It was not really very, because it was a mechanical setup. No? But I will show you more faster. No.
But you guys see that table there with like all those things on it? It took like 4 PhD students just to get it running, just to start it up, right? It was cool though. Wonderful project.
Yeah.
Yeah, I must say, Bernabe, I have to say about this project, this is the most effective EU project I've ever been involved in, the first one. Ever since then, it's been downhill in terms of actual collaboration. But this is the one where it was beautifully constructed by Bernabe and Shichi and Jörg Kramer. I only got involved later so that everybody was a customer and supplier within the project. You know, we were all tied together by these hardware components. So everybody had to supply a hardware component that somebody else would use. Okay, we like being the retina because we were just a supplier. We didn't have to be a consumer for anybody, right? So it's just a wonderful project because everybody was really linked together by developing concrete pieces of this thing. There was no bullshit in the project at all. It was like pure output. You know, and ever since that's been downhill. Like for EU projects, I have to say. I mean, this is by far the most impactful project I've ever done.
And it was very interesting because for me at least, it was like you saw, no, the event-driven structure and the nature, and you have to think differently.
Yeah.
You have to think differently. Yes.
So how hard would it be to recreate that today? Would it be easier, harder?
Well, yeah, today probably we could do that in one FPGA.
No, you would do everything. I mean, what I learned from it, I have to say, make a comment here because this project was so influential. Yeah, what I learned from it was that, yeah, it was hard to do hardware. It was difficult because you had to involve a lot of expertise and it was just complicated getting all these pieces to work. So I just learned, let's just use software afterward. We have a sensor, let's just process with software after that. Just much quicker to develop things. You know, like all of machine vision. So a bit of a, you know, this is a disappointing finding. No, not really, because, you know, we could proceed much more rapidly that way. And when you need hardware, develop hardware, but I must say this is just a beautiful project.
I think it's probably not difficult to fit everything in one Luigi chip.
Yeah.
You have in Luigi you have all the modules. Well, I don't know about the time stamping and all that is special. Anyway, so this was the caveat, no? The pioneering caveat project. And this is about
this.
okay, everybody knows that Toby did this DBS, but now I wanted to talk about So a few years later,
Bernabe, hello, this is Andreas. I'm sorry I couldn't come early this morning to your talk, but I just wanted to say that this is really also a great project to really bring to this community as a demonstrator of solving a problem end to end, and not just solving a little bit here and there, but trying to integrate. And while you're here at Taylor, I try to put things together and really integrate what's going on. Anyway, I think that's my comment.
Thanks, Andrew. So Toby's DBS was 2004 to 2005, I think. Well, during the caveat project, and then few years later, this is a paper from 2013, so it's almost 10 years later. We came up with a very interesting idea to improve a little bit Toby's DBS by adding like an internal voltage amplification stage without mismatch and with a very compact and low power circuitry, which is, I don't want to go into like circuit design details, no, but the idea is basically this one here. So we we are copying the photocurrent. This is like a current mirror. We're copying the photocurrent and feeding it to a stacked diode structure. And then it turns out that the voltage that develops in here has this extra gain, which is the number of transistors that you have here. You cannot stack many, no? Because you will reach the power rate, no? But typically we can put, depending on the technology, but in that technology that we tested first, we could put 4 or 5. And this number, 4 or 5, you square, and this is an extra gain that you get, which will help you to improve your contrast sensitivity with very little area overhead. And actually you can reduce the area overhead because the gain is also given by, is multiplied by this, by the ratio of these two numbers, no? C1 over C2, which are these two capacitors. So in the original Toby's DVS chip, all the gain was just made by this ratio. So he had to use a gain of 20, no? Which requires a large area. Actually, if you look at Toby's pixel, a big part of the pixel area are these two capacitors. No? One is small, but the other one has to be 20 times larger. No? Now with this change, we could change to a ratio of 5 instead of 20. So we could make less area for capacitors. Actually, you can see here the capacitors is just this and this. This circuit is small. You can make it minimum size because its mismatch does not impact it first order, does not impact the performance. And so we could reduce slightly the area and multiply by 10x more or less the contrast sensitivity. And well, we got noise and it's all, but more or less was the same. Yes.
Can I ask perhaps a foolish question here? So is the size of your capacitors what's limiting how many of the pixel elements you can put on a single chip?
Yes.
Mostly, or is there anything
The pixel size. At the end, your pixel needs some size, which is in our case, it was 30 by 30 micrometers. So this is your pixel size. Okay. And then depending on how much money you have, you can make such a large chip with so many pixels.
Okay, and the pixel size is referring to, you see the entire square.
The pitch of the pixels, the pitch.
So that's the entire width of the square, right?
Yeah.
Including all the circuitry. What I'm trying to get at is if you reduce the circuitry, the size of the circuit is a lot, could you put on a lot more pixels on a single chip?
Yes.
Yeah.
So for example, if you can pay, or if you can build a chip which is 3 by 3 millimeters, you can put 100 of these pixels on the side. Okay. Well, you need a bit more, no? Because you need the periphery and the pads and everything. But 100 pixels, 100 by 100 pixel would be 3 by 3 millimeters.
But what I'm saying is, say I was using like smaller gates, smaller capacitors, or whatever, then I could put much more pixels on the same.
Yeah, but there is always
a problem with how much light I'm collecting as well. Like, do I need a certain amount of area?
This piece here in the center is your photodiode.
Okay, and you can't shrink that.
You can, but then you have worse performance, no? Because you get less light. One thing, I've never done it, but I know people do it, is that they build, like, once the chip is fabricated, they build a micro lens over the full area of each pixel that concentrates all the light of the full area into this smaller area. And then you don't lose fill factor. The fill factor is the ratio of your photodiode area with respect to the total.
That's field factor.
And also, Bernabe, and everybody else, most of the images, whatever DVS or regular images today, are face-to-face, where there is a photodetector independent of the circuit. So you use 3D to really stack two chips on top of each other. So that is not really, I mean, that's how it's done today.
Yeah, that's a good point, because actually the Prophecy camera, which is a 1 megapixel camera, it's in 3D technology. So it uses two wafers stacked. And in the top wafer, they basically have the photodiode. The photodiode plus 1 or 2 transistors. And then in the bottom, they have in a more resolution technology, they have the rest. They can squeeze everything in 5 by 5 micrometers.
Since iPhone, every camera that you find in your Android or iPhone is really a face-to-face stack, 3D.
Yeah, because you can do your photodiode with a very good technology optimized for photodiodes, put it on the top, And then the rest you put it underneath in a very like low dimension, like 20 nanometers or 30 nanometer technology, where you can put a lot of devices.
But it's not for free, you know,
It's
these
very expensive.
processes are very expensive.
Very expensive.
Very expensive to make the math sets, very hard to access.
Yeah.
Not really, not really. It's really.
No, it is. You don't know what you're talking about, Andreas. Yeah, so it's more difficult to access than normal CMOS for sure. It's less available. Yeah.
Okay, and here you can see a recording, no? A recording with these, this was a 128 by 128 pixel camera. Here we have two cameras in a stereo setup, and it was observing a pen that was balanced. So you can see the video basically. Now, this is what we are doing lately in this DVS domain. We are looking into foveation, electronic foveation. The idea is that, okay, suppose you have a physical sensor that is really high resolution, like the Prophecy camera, which is 1 megapixel. This one here, this picture is for example, 720 by 360 pixels. So you can build a DVS sensor that has this resolution, or even slightly more. No? But it will also give you a lot of events, no? Because you have small pixels, and it will give you a lot of events, especially when you're driving. No? We saw before, like some videos from car driving scenes. But you don't always need all the resolution all the time. And this is actually something that the brain does, no? Our brain, also our retinas, the fovea is just when you put at the distance of your arm, you put the thumb. This is more or less the size of your fovea, no? The center of the thumb. So it's just a small portion of the whole field of view. So inspired by that idea, what we are doing here in the recent DVS chips that we are working on right now as we speak, what we do is that we group pixels. We group pixels. They will, so we build macro pixels. The physical pixels are high resolution, conventional standard pixels, but there is a way of grouping them, like maybe 4 by 4, and they will operate like a single pixel, but will collect the light of all 4 by 4 macro pixels. They will take all the light, but then only will compute the changes on the aggregation of all this 4 by 4. So by default, we set the whole field of view in low resolution. So if you start with a megapixel camera, it will be like a 100 by 100 pixel camera in low resolution. And then the low resolution information, which is, suppose this is your chip, no, the DVS chip. This is now set everything in low resolution. The low resolution is set to an event-driven low resolution processing system that has some attentional algorithm or attentional mechanism running that will tell you which part of the scene is of interest. Maybe where there is more contrast, or maybe where is something moving faster, or whatever. No, you can play with different criteria. Then once you know the region that is of interest, that region, for example here R1, that region, you ungroup all your macro pixels. So you have, in that region, you have everything again in your physical high resolution. And that region, that small region, the events that come out from that small region, you send to another event-driven processing system, just to do whatever, object recognition or some finer processing. In this way, we hope to significantly reduce the bandwidth, and the content of information that you really need to do something. And actually, you can also define multiple high resolution regions. No, yes.
So does this in hardware?
Yes, that's in hardware.
How does it kind of do that? How does it do that?
How do we do that?
Yeah.
Well, we find a patent that describes it. I don't have a slide describing it. No, I don't. I have a slide that can give you some hint. So I can give you some hint. Yeah.
What is the latency? Because once you detect the attention system, you have to give the feedback, right?
Yes.
So that will limit your height.
Yeah, but that's pretty fast. So this one, I mean, the events, they come out with microsecond or even sub-microsecond delay. Then you need to process them, identify your region of interest. Your regions of interest will not move faster than 10 hertz, maybe. Your regions of interest, even when you are driving, you track another car or a traffic sign, they don't move really fast. So there's plenty of time to move your.
But that's on the separate chip, right?
No, the chip.
No,
here.
this object recognitions and second.
Yeah.
Right? All these are in probably in FPGA or.
Exactly. So this will be sending out events. As the events come out, the attentional subsystem, since the attentional subsystem knows where it has defined the high resolution regions, he can separate the events that are low resolution from the ones that are high resolution. And then you can put like an extra bit to your event that defines, okay, or a few bits, not that define the region of interest that you want to have.
So then, because you have many grouping, sorry, one last question, because you have many grouping over there, right? When you give the feedback, how do you give, because there will be a lot of ports, IO problem would be there, isn't it?
Well, redefining the ROIs or the fovea is slow speed. You don't need like intensive information. The events coming out, for that you really need.
Register there, the
Yeah.
pixel
So reconfiguring the regions of interest is a slow process. No, you don't need to give like intensive data flow.
So this comes from high level processing.
Yes.
Where the region of
Yes,
interest
yes,
is.
yes.
Does this work with moving cameras?
Hmm?
Does it work with moving cameras?
Does it work with moving cameras?
Does it exist? Does it exist?
We haven't, yeah, so far we have a preliminary prototype. But we haven't put it yet on moving systems, right? Right now, everything is done in the lab, static. But yeah, in principle, you can put it anywhere.
I mean, I have to say that most high-speed cameras also have multi-ROI
Yes.
capability, and they are a nightmare to use. They're a nightmare because it's just so complicated to move these ROIs around. Even there was a high-speed camera tracking a Drosophila wing. Just the control of this ROI to follow the Drosophila wing leading edge was just like so complicated and so fragile, because if you ever lost it, you didn't see anything anymore, right?
Yeah.
And so it's just, it's a question of, I mean, now it's a bit ironic that all the camera manufacturers are boasting about how their cameras put out like, a giga event a second. Even like OmniVision Lace Run is like 5 giga events a second. So this is in the direction of saying, oh, that's stupid. Why are you boasting about how much data you can put out when the whole idea is to get rid of redundant data? And this is the direction in the other direction. Just the question is, if it makes the pixel bigger, it's bad, very bad. You always have to make the pixel smaller. So, but if it's just digital circuits in a pixel, then it doesn't make the pixel much bigger. You can imagine some stuff on the edge of the chip that controls these ROIs. And then you have little digital circuit in each pixel.
Or if you go 3D.
Yeah, but 3D is no panacea, right? Because you run out of space there, so you'd like to do other stuff besides ROI, right?
Yeah.
Make
But
better amplifiers.
Yeah, the overhead. I'm going to show some pictures of, the layout of the DVS that we just manufactured. There, we got a fairly big area for the pixel because we intentionally added a lot of reconfigurability to play around.
Complexity.
Yeah, to play around with this first big prototype, because it's a 1 centimeter square prototype that we just submit takeout last month. And yeah, we decided to make a bigger pixel, but to have more flexibility, in controlling and configuring. But if we, for example, had taken the decision that, okay, our macro pixel will be 4x4, that's it, then you can reduce a lot. Right now, in this sensor, we have a lot of flexibility in defining sizes of macro pixels, any shape, whatever.
Experimental chip, yeah.
It's very experimental, yeah.
So another extreme could be scammed from this Piotr, right?
It's what?
Another extreme could be that scam vision, right, which is from Piotr.
Yes.
Already.
Exactly, yes, 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 yes.
So what is driving wanting as small a pixel as possible?
The megapixel race.
That's all. I mean,
You should say what the megapixel race is.
Yeah. But I'm not so convinced in DBS.
In mass production, the megapixel race has dominated CMOS image sensor for 40 years now.
Yeah.
You know, basically you have to fit your chip within a certain optics. Because the optics are dominant in everything, right? You have to, chip has to fit the optics that are available.
like for us.
You know, you don't develop the chip and then the optics afterwards. Your chip has to fit some optics, like in a cell phone. And that
cell
means
phones are
that you need more pixels for the same amount of money.
So is
More
it cell
pixels are
phone-
better.
Cell phones driving this?
Yeah. Yeah, except for like, you know, very low volume industrial applications can afford bigger pixels. Or like automotive can afford bigger pixels. Because they need this high dynamic range stuff, they're willing to tolerate that. But everything is about pixel size, as long as the quality is acceptable. Yeah. The most important thing is the pixel size, because you get more pixels for the same money. People pay for pixels. Yeah, basically, that's the basic story, right?
So you're shooting for cell phone adoption. That's.
Yeah, that's why the cell phones are down like sub-micron, you know, like 0.8 micron, 0.6 micron now. Yeah, their quality is not great, but you get a lot of pixels, right?
Yes.
I want to ask, a lot of the older vision sensors have this like spatial convolution as well, or like spatial contrast, stuff like this. That was also inspired by the retina and so on, and I think the newer ones, you don't really do that anymore, right? It's only the temporal changes that are interesting, because you have like center surround cells or like detectors or something on a low level. Is that also due to just the use of the pixel size, or is there still room, like, is it still interesting, or is it something that
But you're talking about imagers in.
Yeah, I mean, like
DBS.
for event-based imaging, we could also say like on the lowest level, instead of doing a per pixel temporal like change in intensity, you could also say like you have a center surround cell very low level, and then you including changes intensity changes of the center surround cell or whatever, right? So is that something that people still do, or is it something that people have kind of moved away from?
Well, in DBS, the pixel is very complex already. So at least I myself don't want to complicate it more. No? And we can do all this, we can do it afterwards in the event domain, no? With the outputs. No? Right?
By the way, the human retina has very high resolution at the surround also.
Oh, also at the
At the surround, and that helps with 3D motion estimation.
Yeah, but it's more for motion, not for.
For 3D.
Yeah.
So you may want to keep high resolution.
For motion in the periphery, yeah.
Yes, Garrett.
If you follow up on Aaron's comment and also Johannes, so maybe rather than doing a adaptive resolution where we basically pull multiple pixels together for a I guess low resolution presentation, it could make more sense to have a spatiotemporal compression algorithm, right? That could do
space-time.
Yes, space-time compression on the focal plane, and they can do motion, whatever. Right? It will figure out whatever it is.
Yeah, but space is tricky because of mismatch.
Yeah, that's the bugaboo, right? Yeah.
The nice thing about DBS is that it's the temporal contrast, and you subtract the random offset.
Well, there can also be some kind of spatial differencing.
Doesn't work. Yeah.
We tried it in the past, and it was a nightmare. Yeah. We had to calculate.
Yeah.
Yeah, so maybe that you can do it more efficiently once you have the events. Once you have the events, then maybe you can go to spatial processing, doing convolutions and so on. Yes.
Yeah, so is this basically a homogeneous pixel sizing, or you have a distribution of, it's in a sense homogeneous? Okay.
We might comment about this so somebody doesn't go down this rabbit hole that in the past there were multiple attempts to build foveated retinas, like where you have high resolution in the middle and lower resolution on the side. And then you would put the thing in a pan tilt system and move it around. Those are all complete failures. Because of the complexity, mechanical complexity of moving. The brain has to do it because the brain can't multiplex well. You have to move the eye around, right? You can't electronically multiplex. In electronics, you can electronically multiplex anywhere instantly. So it's a different story, right? It's just simpler to design it. You don't have the mechanical complexity of including a moving eye. Yeah, it's just easier to do it, you just build a uniform array. So all those foveated retinas, were maybe like publication success, but they never had any traction commercially.
But in the previous talk, we heard how many events are generated. And that would.
Then you should include very minimal circuits to limit the redundancy, to control, to reduce the redundancy, right? Yeah.
Yeah, we'll
Minimal,
see.
right?
So
You have
once
to be
we have-
tasteful, very tasteful.
Once we have these sensors operating and because this is in a big European project in FPAA, we do the DBS, but then there are other people that do all the processing and attentional mechanism and all that. And once they put their hands on the sensor, then we will see the advantages in real time.
I was gonna ask, so regarding kind of 3D processing and processing in the event domain, have you done any work of kind of on like the second layer of your 3D stack, just receiving the events from the pixel and then kind of processing either temporal characteristics or like local 3x3 neighborhood type things in the event domain at like a pixel level?
Yeah, the problem is that when you go to the next layers, there is an explosion in like processing modules. So we'll see here, for example, you can see that. So you're saying sorry. So you're saying you would like to stack in 3D all this.
Not necessarily just something to do, like say denoising or.
Yeah, you can do something
something
simple. Yeah, something simple. Yes, where you have the same dimensionality than the sensor.
Yeah, exactly.
But once you go to the convolutions and so on, first there is an explosion and then there is a contraction in the sizing of your space. Yes.
I wanted to ask a follow-up question about the pixel race, count race. If you can cheapen each DBS pixel, then you can fit more pixels, right? But you still want all the dynamics inside the DBS pixel. Can't you pretend, and this might be a really stupid question, but you pretend all the pixels are like your rods and your cones, and then each your spatial temporal circuit or whatever is now receiving from a population of rods and cones. So you can still claim that you have, so you can use like a normal active pixel, which is much smaller than a PBS pixel, and still get all the dynamics that you want on a second layer or something like that. Does that make sense?
I don't quite get it. So you're saying do a physical sensor that is frame-based and try to.
Well, if you want more pixels,
Yes,
then you want to make those pixels as small as possible.
yes.
But you then can't fit all the dynamics of this DBS stuff, right? But if you have two chips, right, you bond the first one, which is just all your many megapixels. And your second one actually has all of your dynamics, but they are receiving inputs from maybe whatever the ratio is from rods and cones to ganglion cells. Then you can have everything that you want and still claim a gigantic pixel count. Is that?
Yeah, but then your first chip is.
Bernabe, I think what Leo is asking is, can you make metapixels, which have individual components, but they share some processing?
Yeah, where the processing is in another layer on the right.
Yes, in 3D. Leo presumes 3D, yes.
Yeah, but it depends on if it is a simple processing, yes, it was like the question before. Like for example, maybe this little module here, which is very simple pre-processing, that you can stack in 3D with this one. Yes, but not the full thing.
Yeah, but by the way, you should be aware that there are high dynamic range image sensors that also have a mixture of high gain and low gain pixels basically within the array, or they expose multiple times within the frame to get bigger dynamic range. Everything is still open for exploration there, and all those ideas are still worth thinking about, right? And industry is thinking about them actively. Like you have no idea how active the exploration of this kind of space is industrially because of the competitive pressure to provide higher image quality, higher dynamic range, higher frame rate. It's a very active field. And it's at the circuit level, the device fabrication level, process technology level. I mean, the image sensor business is a $20 billion per year business, 20 billion per year or more in all field of image sensors. So there's a lot of money going into R&D, right? 20 billion is a lot of money, right? Isn't it?
It's exciting to be in the field, and the NIC group will focus on perception, including some new sensors next year.
We couldn't hear you, Andreas. Okay.
Next year's focus is.
So I want to ask a question. So it sounds to me like what the limiting in the race to megapixel thing, the limiting factor is how small you can make your photodiode, what's picking up the.
Not the photodiode, everything.
Everything. But if you're stacking it in 3D, then I'm assuming, and the circuits which are doing the processing, you can make them quite small, right? As you decrease your transistor size or whatever, I'm assuming you can make them smaller. But from a physics point of view, your photodiode has to pick up a certain amount of photon to be able to detect the imaging. So what I want to ask is how efficient are the photodiode, but obviously with an integrating camera, you can collect the photons over like a longer amount of time. So what I want to ask is how efficient are they? Do they turn all photons which hit them into photocurrent? And is there like research into different materials for making them, and like what's going on with that is what I want to ask.
Yeah, that's a really good question, but I'm not an expert in photodiode technology. I don't know if you know more.
I know more about it, but I'm no industry expert, that's for sure.
I can tell you I'm really amazed by how they keep shrinking the photodiode size in your mobile phones. I think the chip is less than 1 millimeter square, your camera chip. They have what, 20 megapixels? So 1 pixel is capturing just a fraction of the wavelengths, of light. But they still can. Yes.
So you can make a photodiode with internal gain. First of all, for very high speed, your size of the phone, you need to be able to capture enough photons to really be able to respond. So typically for very, very high speed cameras, photodiodes are about 20 micron, 18 micron is really the commercial cameras they shoot films in the video industry. But then how do you get smaller and gain? You can actually make a photodiode with internal gain. Therefore, you don't add noise, because anytime you do anything else, you're going to add noise. So you add minimum noise. We can discuss this in the NIC group if someone wants how to make photodiodes for specific areas.
Yeah, so far we've been talking about, doing the pixel and processing in 2 separate layers. But is there a possibility to extend just the pixel to 2 layers, such that you have the photodiode, density in the first layer being much larger, and you don't necessarily have to worry about pitch matching in the second layer. So let's say you move the amplifier in the DBS to the second layer.
That's what they do now. That's what they already do.
That's what we do now. I mean, that's what everybody does now. And the pixels don't even have to be the same. You can have an ultra wide dynamic range pixel. You can have a single photon detector pixel, and they all look like a uniform mosaic, because you can fan out the wiring from the second layer to the first layer. That is exactly what's happening now. That's the state of the art.
And you use the same photodiodes as traditional cameras use, or do you have to use?
Yes.
The photodiodes are the same.
Exactly the same.
Exactly the same. Exactly the same.
Yeah. So we are poor people. We use cheap technology. Photodiodes are not very good. Right?
Is there anything for IR anybody's doing?
Yes.
Yeah.
Yes, there is the same thing for IR.
Technology. But
You can do actual, I mean, the near infrared, you get it for free in CMOS.
Yeah, but is there any technology available where we could use IR or
Which
Yes,
IR?
we are designing chips.
Short.
short IR?
We are designing chips for IR.
No, sorry, it's the other side of it.
Then it's difficult.
We need another technology for the
Yeah.
photo detector,
Yeah.
because it's germanium,
There's a company in Colorado Springs that does.
Yeah.
SWIR. Sort of.
It's exotic. Let's call it, it's exotic.
It's exotic.
That's what I'm trying.
Or you can do micro machining and build microbolometers in each pixel. That will capture very long infrared.
The most interesting detectors today for IR, for near, for IR mid wave, aside from mercaptyloride, is really some silicon detectors where they implant some extra materials in the pixels. We can talk about that. If someone is interested, come to the NIC group and we'll have a discussion group.
Other question? Okay, so this will answer very quickly one of the questions that they were, somebody was asking, okay, how do you group your pixels? This is how we do it. So we use the one that I showed you before that has increased contrast sensitivity. And it turns out that if you short this node, the output node, if you short it between neighboring pixels, your output actually represents will do the same computation on the sum of the photocurrents of all the pixels that you short in this point. And this you can write down the equation and it's easy, it's easy to show. But you need this structure here. You need this structure, and in this structure, if you short this node between neighboring pixels, you are computing here. And now here you do this difference or change detector circuit. You will get events that represent the change of light for the sum, not the photocurrent of one light, but the sum of the neighbors that you short. And this is what you get when you do that. And this is how we do it. This pixel. There is a catch, because when you group pixels to have low resolution, you lose the high resolution. Right, because you're grouping your pixels. So whenever you have a phobia, so this part you put in high resolution, and this part you put in low resolution. Here you cannot get high resolution, but here you cannot get low resolution, right? Because you either group or ungroup. But we just find the pattern where we solve that. And I'm not going to talk about this today. But there is a way.
That's very annoying, Bernabe. That's like one of Riyad's talks.
Well, maybe I can talk now because we already deposited the pattern. Yeah,
It's okay.
I got confirmation, but we can do it offline.
So what is more complicated than just opening and closing the switch?
No, it's a bit more intelligence.
Another possibilities might be if you just have randomness there, you have random connections across the field, right? Then you can do some computer sensing based reconstruction where you can have this high dynamic, high resolution in one area, small resolution.
Yeah, time multiplexing.
Yeah, that could be another.
That could be, yeah. Yes. Okay, so the idea is that you short this node and then you can group and get the high resolution and the low resolution. So this is the first prototype that Teresa designed and tested already. It's unpublished, no? So we submitted the paper already.
We're preparing the paper.
The paper is almost ready.
It's almost ready.
But you can see here. Here everything is in high resolution. Here everything is in low resolution. And here only this region is in high resolution. This is low resolution, high resolution. So,
It looks like there's difference between the high resolution in the red frame and the corresponding area on the left.
Yeah, because it was captured at different times. No? It is not like the same. She was trying, yeah, actually, here you can see the teeth, right? You can see the teeth, here you don't see the teeth. So, because it was different moments.
One way works, she's married.
And this is the new one that we just taped out last month. This is 300 by 400 pixels. This one was 128 by 128.
Which technology?
This was AMS 350 nanometer. And this one is XFAB 180 nanometer. And this is 1 centimeter square chip. So we're doing full wafer. Yes.
About the videos image. So why is only the face in high resolution and not the object?
What?
Why is only the face in high resolution and not the object?
Because this is what we decided to put in high resolution.
But,
You decide the region.
Yes, here the configuration is done manually. It's not done with any intelligent algorithm. I just put manually some region. We have resolution, so it's not.
But I must say that with DBS, it's much easier to like track a bunch of objects. It's a very cheap tracking algorithm, so actually controlling these ROIs is going to be much easier. Because you have this very simple tracking algorithm that will track a bunch of objects and tell you the size approximately. So controlling the ROI is going to be a lot easier than traditional high-speed camera.
We're working on that, on taking the events, do some tracking, and do automatically the configuration of but this is ongoing work.
Yeah, but I have to say on the contrary to that is if you're trying to use the ROIs to track a bunch of objects, those are the only ones that are going to be making events in the first place. So why do you bother making ROIs for them? Because they're the only ones that are going to be making data. So you don't need to program ROIs because those are the only pixels that are going to make data in the first place. So it has to be in a more complicated scenario that this has value.
Yeah, when there is a lot of events and when you see the full scene.
Yeah, you're driving or flying or something like that, yeah.
And then you have maybe in that case you want to focus on the regions that have slow motion, not fast motion.
Yeah, maybe. That's true.
And discard the high speed motion. Yeah. Okay. Another interesting thing about this prototype is that we have 4 AER readouts. So each quarter of the array has its own AER readout. So you can improve a little bit the speed. Okay, let's see if I still have time. Okay, let's now go into event-driven convolutions. So this actually, the first time we did it was also during the Caviar project that we did dedicated convolution chips. The way of doing convolutions in the event domain with physical hardware is as follows. You just need an array of integrate and fire neurons. And you send to this array, you send, for example, the events that come out from a sensor, from a retina sensor. You send out the events. But when you have an event of coordinate XY, which is maybe this center here, instead of sending just one event to that coordinate, we stimulate a neighborhood of this central coordinate, and we make a contribution in the neighborhood that is weighted by the convolution kernel. So there is some circuitry in the chip that, for example, if you are here, you provide a packet or a contribution, a weight to that pixel that depends on this convolutional kernel for that position. And then event after event, you will be computing the convolution of your input flow with this convolution kernel. And then the output event of this chip would represent that convolution dynamically. It will not be frame by frame, but
this is a space kernel.
This is a space kernel, yes. It's a space, yes. So what we have here, the way we do it in this chip is that the events come in here. And maybe that event has this coordinate, XY. We have here a kernel round in the chip. Here you can have several kernels like this one. So you have here the weights for the values. And then what we do is that when we know the coordinate, we copy row by row, the weights, we copy them to the area of your convolution kernel. And then each neuron here is incremented, it's integrated, it's incremented by the weight that is stored in this kernel. And then we can have multiple kernels. And here, for example, the address, depending on the origin of the address, you can pick one kernel or another. And you would do multiple kernel convolutions with the same single chip. That's also possible. But this is the basic idea, that for each input event, you just stamp the full kernel on top of your integrated fire neurons. And this event after event will compute your event-driven convolutions. And here on the right is a recording from the Caviar project. This is the output of the camera. I don't know if you can see, not very good, easy to see, but there is a PhD student, Patrick, PhD student from Toby at that time. He was juggling, no? With he was very good in juggling, so he had 3 oranges and he was juggling. And we programmed, this was fed to a convolution chip programmed with this circular kernel that would detect the center of the oranges. And this is the output. You can see that the hands and the fate and everything is fitted out, and it is just tracking the output or the oranges. Yes.
So I just want to be clear if I understood it right, because normally if I have a convolution, I have let's say you have a 5x5 kernel there. Let's say I have a 5x5 input patch. I apply my 5x5 kernel to it, and I get one output. I get one convolution output in the next layer. But here actually you receive one event, and then the weights that you look up is actually from the different kernels that are strided, right?
No, one kernel, which is just a circle. In this case, it's just a circle. It's like a Huff transform, right? Think about it. Well, that's a bad way to describe it.
No, yeah, but I know what you think. Yeah, normally when you think of convolution, you have in the convolution plane, you see a receptive field, right? From your input, there is a receptive field, and you take that receptive field, you weight it, and you update your single pixel in the convolution plane. Here we're doing the opposite. There is a projection field.
Projective kernel, right?
Exactly. Mathematically, it's the same. I mean, if you work out the summations and everything, at the end it is the same. But in the event domain, we do it with projection fields. So for each pixel in the input plane, we project the kernel to the convolution plane. But then since we will have many events coming in, at the end it will be the same. Of course, we don't sweep the input in the input plane, no, because it is sparse.
But do you weigh by time too?
No.
No.
The neuron does. In a way, the neuron has to be leaky.
It is leaky, yeah.
It has to be leaky, otherwise it doesn't
leaky,
work.
yeah.
Right.
Okay,
Because-
so the earlier ones have
Yeah.
decayed.
Yeah, for example, if you want to detect a circle, then the features forming the circle, they have to come in a given time window, which is controlled by the leakage.
But you can just be integrated via neurons, and then you just care about the order of events and not about the timing anymore.
Yeah, but if you have a circle that you want to detect, and you have in your retina, suppose you have 100 pixels that form the circle. The convolution chip has to detect these 100 events in a given time window. You cannot provide like half the circle in 1 second and 1 minute later the other half circle. So it has to be simultaneous. Everything has it's a simultaneity detection. So they have to come in a given time window that you define, depending on the speed of your seed.
And just one more question, like if I now again do this comparison between like image patch and receiving an event. If I receive one event, let's say 5 by 5, if I receive 5 by 5 events, then I do essentially 25 times the computation. But if I'm not sparse enough, it doesn't pay off to do it later. Right?
Yeah, but this chip is very fast in projecting the kernel on the rows. So the events come in maybe at 10 megabytes per second, and the chip can update this window. It can update it in less than 1 microsecond actually. For bigger kernels, I mean, the kernels could be for the chip that we manufacture, the kernels could be as big as 32 by 32. And for that, it needed about 1 microsecond, between 1 to 2 microseconds, to update the full 32 by 32 integrated pioneers per event. So the chip was really fast, and I still have ideas to improve that. No, but I haven't had time to try.
I mean, in a way, it has a scaling problem, right? Compared to CNNs, it doesn't scale well, this approach. So it's for simple kind of detectors, right? Where you have a template of the object you want to see. I think, Bernabe, it doesn't, compared to CNNs, it doesn't scale properly, this approach. Well,
Yeah,
okay, we
we
can
need the
argue about
space.
that, yeah.
We need the
We
space,
can argue
yes.
about whether SNNs make sense,
Yeah.
yeah.
It was pretty much the same question. So isn't here the time that it takes to copy, it depends on the size of the kernel that you're using, right? So as you say, array up, like at some point, this is going to be the limiting factor. And I just want to get a feeling for it. We are already at the point where this sort of computation is giving the limit to how many events you can process, or if this is still
Yeah.
fast enough.
So there is an event throughput that depends on the size of the kernel. But if I remember correctly, for the chip that the latest chip that we manufactured, it was like this: for 32 by 32, which was the largest kernel, the event rate was between 1 to 2 microseconds, which is close to 1 megapixel anyway. The peak, actually, the peak of your event rate.
But now, do the kernels need to have 0 weight altogether? Do they need to have a negative?
Yeah, they can be positive or negative, yes.
But do they need to be 0 sum?
What?
0 sum across the whole kernel. In other words,
No, you are free to set them.
no, but if it's only positive, then any input will eventually make the neuron spike, right? If it's only a positive kernel, even noise will make it out because you don't have anything to suppress the neuron that's receiving it.
No, but noise gets filtered out with the convolution.
Okay, but
Yeah, the noise events, they get filtered out.
it needs to have a negative, it has to be inhibitory, not just excitatory.
Have leakage.
Yeah.
I'm saying the kernel has to be balanced, positive and negative. In practice, at least when I look at stuff in software, you always have to have a balanced kernel. Otherwise, you end up that just any input will eventually make the neuron spike because you're only getting positive input
No,
from the
but you have
kernel.
the leakage. You have
the leakage.
What?
You have leakage, so they.
You have the forgetting time of the neuron, that's true, but.
In the one that we implemented, we had positive and negative weights.
Yeah.
Is that really necessary? I think it's not really necessary because you can separate it into 2 parallel convolution chips, one for excitatory and one for inhibitory, and then combine afterwards.
Yeah, but then you still have the negative, right? Effectively. Anyway, let's go on. Yeah.
Is it possible, like you have some event rate coming in, is it possible with like say a bad convolution kernel that you get more events coming out? Than you have
Yeah,
coming
of
in?
course. Yes.
So the kind of throughput limit is both like a function of the data coming in and the actual event rate, right? Like you could imagine some like particular case of input data or input events giving you a really bad output case. Your output can't handle it.
It depends on what you want to do. It depends on what you want to do. Yeah.
Sorry.
Okay, good.
Okay, I can go first. So, if you want to implement different kernels here, right? Typically, you have many feature maps in a normal image processing network, right? So, does that require you, like, how would you multiplex it here? Because that means you need to copy the neuron state again into some RAM if you want to go on different kernels, right? Or would you just replicate the entire structure here?
You can do if for example, if you have I will show it later on. But if you have several input sources coming to the same convolution module here, depending on from where the event is coming in, you pick another kernel. And depend if it's coming from another plane or whatever, you pick another kernel, but everything is then updated in your feature map.
That's assuming that you're summing into the same neurons, but often you have like different output feature maps. Like there's a dimension you want to have different channels in an image, like in an input layer, for example. And each channel would apply a different kernel to it. So that would, in this case, either require you to have like to also move all of the neurons internal states into some RAM if you're multiplexing this, or it require implementing this.
You just accumulate them all together. I think I have a picture for that later on.
Sorry, anyway, just quick. So one last one.
Yes.
It does become prohibitively expensive to use graded spikes instead of binaries as an input. If so, then you have to add a multiplier.
Yeah, because somehow you would need like to scale the weights, you know, when you. Well, if it is a factor of 2. It would be trivial because you just, when you copy the kernel, you just shift left or right, no? By multiplying by 2. So that would come for free. If it is not factor of 2, then you need something else. So here, for example, here is a very simple illustration of a 2-kernel process. So we have we have a very old oscilloscope, this phosphor-based oscilloscope that we are putting 2 sinusoidal amplitude decaying signals or amplitude increasing signals in XY mode. So we see a spiral on the screen. Do you understand that? No, if you have 2 sinusoidal signals, okay. And you see the spiral. You can increase the frequency of your sinusoid. You still see the same. No? So in this case, the spiral was 5 kilohertz spiral, no, or rotating. And now we put the DBS to observe that. No? So in practice, there is the electron beam is physically doing the spiral. No? And when you record that with the DBS, you actually see, I mean, when you lay it back slowly, you see the spot doing the spiral. So here is a recording at 300 microsecond. Oops. What do I do?
The right arrow at the bottom.
Yeah.
No, close to the bottom.
Okay, so this is X, Y. This is the plane of the sensor, and this is time. So in 300 microsecond, there are like 3 or 4 turns, no, of the spiral. The blue dots are the outputs of the retina. So you can see that in 300 microsecond, there were quite a lot, no? Several hundred probably. So if you could track with very fine time resolution, it could track the spiral very neatly. So these events, for the events coming out of the DBS, we have the X coordinate, the Y coordinate, the sign bit, and the K bit. The K bit was, it was just 1 bit to differentiate the events coming from the sensor or coming from the output. So here, and this was hardwired, no? So we put this bit to 0 or 1. No? It was hardwired on the PCB. So the events coming from here had, for example, K equal to 0 for the DBS. And the events coming out from the convolution kernel, they would fed back, and they had the other K, maybe K equal to 1. And these events were merged here. Well, this is a merger that simply time multiplexes as they flow in. No? There is a handshaking, and then they are mixed in the same bus. So here we have a list of events that is the X, Y coordinate, the sign bit, and the K. The K tells you if it is coming from here or if it is coming from the output. And then the convolution chip would pick either this one kernel for the events coming from the sensor, or a Mexican head kernel, which is a winner-take-all kernel. So it would do like competition between the neighbors in the output plane, in the second layer. It would do competition among neighboring neighbors. And the one in the center would like be enhanced. And what this was doing is basically enhancing the center of the trajectory. So the cloud of events was The information was reduced because we get very few events. You can see here there are 1, 2, 3, 4, 5, 6, 7. So probably between 10 to 20 output events in these 300 microseconds. That will give you the center of the spiral. And if you represent that, for example, here is the y coordinate, and this is 10. You can see the delay, no, between the events coming out of the retina and the events out of the convolution chip, and it was in the order of 10 microseconds, no, the delay between the events of the retina and the tracking of the center. The 10 microsecond delay, we were doing 2 convolutions on the input flow. And we were doing the 2 convolution on the same plane, because all the integrated, there's just one array of integrated fire neurons. And you mix together the 2 convolutions because you do it event by event, coming from different origins. You update with different convolution kernels, so you have like the sum of the 2 convolutions in the same plane. No? It's like a feature map extractor. And this you can generalize to a generic convolutional neural network. No? You have here the retina, then you have your first plane with different convolution modules. Here you just program one kernel, no? Because each convolution module just is receiving events from a single source. But in the second layer, you also have many convolutional modules. But now each module can be receiving events from different other original modules. And for each one, you can define a different kernel. This is what convolutional neural networks do. But when you do it event by event, you just need something that tells you, okay, this event is coming from here, so I pick kernel K1. This event is coming from here, I pick kernel K2. And you update simultaneously one single array of integrated fire neurons, and you get the computation of all kernels superimposed. You get your feature map, basically. And this you extend to as many layers as you want. And the interesting thing, which is illustrated here, is what we call the this pseudo-simultaneous property. What does it mean? Here, for example, I'm illustrating, this is just one convolution module that is programmed with a vertical Gabor filter. It will extract vertical edges from the input flow. So the retina is watching 2 people walking, like here. No? There are 2 people walking. But these spikes are fed to one simple convolution chip programmed with a vertical Gabor filter to detect vertical edges. And this is the output. So you can see it is showing you more or less the vertical edges. But these are events collected during 40 milliseconds. And also these events collected during 40 milliseconds. But they are the same 40 milliseconds. So we are feeding events to the convolution chip. The convolution chip is dynamically providing events. And during the same 40 milliseconds, we capture both this and this. So these events here are shown in time, 40 milliseconds, and these events here in time. They are also, there seem to be less events. Actually, we have 500 spikes in this picture, and here we have 1,600 spikes. And they are superimposed. Why? Because for the convolution chip to produce one spike, it only needs to receive in the range of 4, 5, 6 properly aligned input events. As soon as it receives 5, 6 vertically aligned events, it will give you an output event. And it will give you with microsecond delay, unless the events are there. And that's why it is pseudo-simultaneous, because you don't, it doesn't have to wait for the full picture to take the picture, compute the convolution on the picture, and give you the output picture. It will do event by event. So it's really fast, because the events are produced as soon as there is enough information to know that there is an vertical edge at that location. So this is pseudo-simultaneous, which means that if you cascade that, more or less everything is pseudo-simultaneous. So if you if this convolutional neural network is programmed to detect, for example, I don't know, a 0 from the MNIST data set, as soon as there are enough events for the whole system to detect or to tell you that, okay, this is a 0, it will give you that 0, even if the input image is not fully loaded. Not all the events are there, but as soon as there are enough that are good enough to tell the system, okay, this is a 0, then the system will tell you. Doesn't have to wait for the input picture to be fully provided. And the other thing, you can see here that noise is filtered out when you do convolutions, because here you see the input, there scattered noise, and the noise disappears, because it is computing vertically oriented edges. So if there is noise, it's not vertically oriented, so it will disappear. So yes.
Does it mean if you have another filter horizontally, you combine the two, the noise is gone?
Yeah, then you can.
And you have the original recovered.
Recover. Yeah. Maybe not exactly, but a representation.
Yeah.
Yes. 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 And this is actually what we do here in the poker card recognition experiment. So this is the DBS camera. We can see it here. Here we can see what it is observing, and this is a poker card deck. It's a special poker card deck, also it's custom made. When you can see it, you can see it. All symbols are black. This is to enhance the contrast. Because
this is trickier than it looks. Do you see the deck of cards? What's funny about that deck of cards? Anybody notice what's funny about that deck of cards?
there are no reds.
Besides all red cards are gone and no face cards. What else is funny about that deck?
The suits are mixed.
No, that's not what's funny about it. What else is funny? You have to read. Bernabe wrote a beautiful paper about this. He said exactly how to do this. Right? Not everybody ignored this advice when they tried to do this experiment, including me. Do you see what's different about this deck of cards?
No face cards?
No, I mean, it has no face cards, but what's different about the cards? Yeah, the aspect ratio. They're very long cards, right?
Yeah, there are two cards together.
Yeah, why are they very long like that? Produces.
So this is in one piece. Oops.
To make the symbols move across, right?
No, to grab it from here, because I'm grabbing the lower half and moving the full card. So the full card is moving. If you do it with a commercial card deck, you have to grab the card deck somehow, and then you can only move like the upper part. No?
But it's also to make the cards move across the picture, right?
Yeah.
I mean, this is much harder than it looks, because what you're seeing, every time you get a new symbol, you basically see an after image of the old one. Problem, in other words, the output depends on the previous card, right? Because you see an after image, so it's much trickier than it looks, right? To get it to work right. If you want to recognize a particular card, you have to do it in the context of what the card was before, right? So it's not so simple.
And also it was tricky because, I mean, you see, one can browse the full card deck like in less than 1 second, actually. You do brrr, but then it will produce a lot of events, and it was actually saturating the grabber, the event grabber, which is down here. Because this event grabber, the limit was between 8 and 9 mega event per second. So we had to put the contrast sensitivity actually very low or very high. So that it had like low contrast sensitivity to limit the bandwidth, the throughput of events, but still have enough information to detect the symbols. And this is what I'm showing here. So this is a playback in real time. This is JAR. In JAR, here you can see the frame time. So here frames are built every 20 milliseconds, more or less, which is real time. So it collects events every 20 milliseconds, makes a picture and shows it on the computer screen. So this is real time. This one is the same recording, but in slow motion. So now the software is building a frame every 70 microseconds. Every 70 microseconds, it stops building a frame and shows on the computer screen. So you can see the fine time resolution. And now what we do is that we track a symbol. we look at one symbol and track it. Here you can see the flipping of cards, no? So you have one card that goes from the top. You can actually see the edge, no? The edge of the card. Now comes the next one. And during some time, the two are visible, no? The previous one and the next one that is coming afterwards. No, you can see them. So in the next one, so now we make a little window here, like a tracking window, which is 32 by 32 pixels. This foot is 128 by 128, but now we track 32 by 32, and we feed it to a convolutional neural network with 3 layers. So it is actually similar to a LeNet from Jan LeCun, a LeNet network, and it was trained to discriminate between the 4 symbols. And this, here we can see both the input and the output. So this is the input, which is the tracked symbol, and this is the output, the recognition output. Actually, to show the recognition, what we did is that, because here you just get events, no? There are 4 output channels that is telling you events, no? Just spikes. But in order to regenerate the symbol, what we did is that we fed, for example, this output was fed to a simple convolutional module whose kernel was the symbol. And it was configured in such a way that every time there is an input event, it would send out the full convolution kernel, which is the full symbol. So we would see, for each input event, we would see the full symbol simultaneously. And then we could capture it with our PCBs and display it here. So this was actually fanning out, no? For each input event, we were getting like, I don't know, 30 or 40 output events, no? To build the symbol artificially so that we can see it. And you can see that it was recognizing correctly, no? You have here diamonds or hearts. Then we get the output, recognition output. And then here is a capture in time, space-time. So this is time, 20 millisecond time. And you can see that here are the events of one card, the recognition of diamonds. Now the card flips from one to the next one. And in less than 2 milliseconds, there are already output events of the new card. Because it just needs enough events that represent the new shape. Okay.
Okay, I think
It's time to stop. Yes. Okay, good. So, yeah.
People virtually, hopefully you're picking me up okay. I'm gonna double check with Terry and make sure I got that. But yeah, definitely wanted to talk about the sort of sense of physical computing, primarily on the analog computing side, and talking on energy efficiency. Talking about a lot of things that looked at over the years. A little bit towards the end, I'm going to talk a little bit about where some things are, might be a little bit fast at the end, just to get a picture and those can be talked to themselves. But we kind of want to look at this a little bit. When I talk about physical computing, I mean computing that effectively the core engine is computing over real values. And so that's always kind of interesting space and generalizes a lot of things. So, cool. A lot of hardware people here, so some of you will know what I'm talking about, and some of you may not have seen this before, so that's cool. So when I started talking about computing, of course, we had a really nice sort of historical overview, thanks to a couple other people gave some points on this. People are at least familiar with Carver Mead. Who's referred to, in full disclosure, he was my PhD advisor. I think I was the youngest, the last one out, so that means whatever it means. And there's an interesting thing though, when we were doing neuromorphic design, I'd say in the 80s and 90s, the question that everybody feared, and I mean feared, okay, is this question of you show your wonderful work, you present it, and then the next thing somebody would say to you is, yeah, but couldn't you just do it on a DSP chip? Why'd you bother? Okay. I agree that over time, that question may have evolved a little bit, but that was part of where some of the conversation began.
So now what's this, GPU, right?
Well, people will talk about a different processor, GPUs, different things, and I think all these questions are relevant. So there are 2 questions.
What's it? Yes. I gotta ask that question yesterday.
What is that?
Sorry, I gotta ask that question on Wednesday.
What's the DSP chip?
Or no, can't you just do it?
Yeah. And DSP chips was actually a very big deal throughout. Basically was what drove a lot of the cell phone concepts and so forth. Eventually, it was the first killer app of it. Well, it was the second, many level killer app. First DSP app everyone usually assumes is Speak and Spell, and if you know what it is, that already dates you. And that sort of had its genesis primarily heavily hardware side from TI, Texas Instruments, Gene France. And I'll bring in one or two comments as I go. Well, one of the things that came out, this was a bit after sort of the analog velocity neural systems book that some of you may know about. That was in 1989. Gregor had another paper, wrote a paper in IEEE proceedings saying, there's a whole bunch of levels of energy efficiency. There's a bunch of things in that paper. I don't need to go through everything. But one of the beautiful parts of it was, it's like, actually digital should be. You're hearing it? Oh, I figured, yeah, that's okay. I understand. I figured, I'm a soft speaker, so you guys might appreciate that. But the question was like, wait, there's a certain energy, analog should be more efficient than digital just on sort of a transistor counting argument. He made the argument from a multiplier, 16-bit multiplier, and kind of said, it should be that's just for a factor of 1,000. Actually said thousands. Okay, fine. And the size should be, 100 range because the transistors aren't quite as, are a little bit bigger maybe. And so it's kind of like those kind of conversations. So this was an interesting hypothesis. I will admit that this was probably not the thing that most of us were, even when I was there, this wasn't like the first thing in our mind, but we did kind of talk, we started to go, well, how are we ever going to address this question? Because that question kept coming up, right? Those of you from older times all agree with me, I guess. Good. So cool. So this factor of 1,000 is an interesting question, and generally the assumption most people are like, yeah, Carver, that was good. Whatever. Although I will argue Carver was probably more ahead of his time than the rest of us, which we felt right. So we take that and you go, well, okay, how did this kind of get definitively looked at? And and there was a different couple of pieces, particularly when you look back on it now, a couple of different pieces of work where people kind of said, yeah, actually it does look like there's some improvement in energy here and so on. We can talk about those. But I think the undisputed question at some point eventually was in 2004, this paper that actually came out right out of CSCC, which talked about the computational efficiency. So it meant that how much computing per unit energy really did give you that factor of 1,000 improvement. And this was directly compared against the DSP chips at the time. There's interesting stories about all of this, of how this all came about. Obviously, the hardware part worked quite nicely. The conversation on the DSPs was actually a little bit less than this, so it was more than a factor of 1,000. This partially came out from the fact that we had a very strong tie with the DSP group at TI. So we actually knew the designers. And there was a lot of different conversations to have been had there at the time. So these were not like, we didn't fudge any of the numbers. They looked at it too, and they're like, yeah, no, you're right. And so, and I will say there were some, with all things, right? There's a little bit of like things that build up to this. And then there's definitive things, and then just from that point on, the conclusion is clear.
It's still 16 bits.
That's the way that's the way for this comparison. And it was actually looked at for the DSP ones that were in a certain space. So the comparison that Carver actually talked about is 16. The equivalent behavior on the VMM would have been at that level, although per device was more like 12. But analog numerics actually get better when you do these things. It's a whole numerics question. I'm going to leave that sit for the moment unless anyone wants to jump on it. So it's actually fairly fair comparisons. What got interesting, so once you look at that, you're like, okay, we've got at least a data point. And then we kind of figure out, we keep looking at this question again and again. And then it became another discussion, and this was actually also turned out to be things that myself and actually two other individuals. This actually came out from a conversation from Bill Maher's original PhD worker who was looking at asynchronous digital design, and he wanted benchmarks. We're like, okay, and we actually had known some of the stuff of what people were doing digitally at the time. And so, normally you get wonderful plots of Moore's law like this, right? Wonderful. Everything scales with years in those days. And then it kind of started to stop, and there's a lot of interesting conversation there. Well, if you zoom into this space up here, this is what you see for the graph, and as well as a whole bunch of different processors where you could actually look at the computation of the units of time. And we started realizing in general the efficiency was flattening out. Now, we did a bunch of things here. Make sure we kept everything in 32-bit MAC operations. Why MAC? Well, one, because it's what we do for that structure. Two, it actually had its roots in the DSP processor concepts in the day. Because then you could really say, this is what the computation is doing, and we can be very precise. You'll never see me use a MAC as by the multiple accumulator if I didn't define it. And the other side of that is that if you do ops or flops, you get a mixture of operations in there. And so that mixture gets played by every computer architect of how to talk about their system. And remember, no op is an op. And so we're very, very careful on looking at these kinds of numbers and trying to look at this cross process. And it really looked like there was kind of an energy efficiency wall as we're looking at that. And it was flattening out, and people might go, well, why was it flattening out? And actually, one of the most important parts, by the way, first thing is this is across all yielding chips, not one-offs. Second, and that actually gives you the key, is it actually had to do with mismatch. And to be fair, since then, this is probably people got a little bit above it and so forth, but not by much. And this has actually been relatively predictive over time. The interesting thing is what you see a lot of people do is go, well, 32-bit operation is this expensive? I'll go to 16, I'll go to 8, I'll go to 4. And these things scale quadratically and maybe a little bit more depending on what you're doing with it. And so this is how you kind of look at this. Everything we try to be really, really careful in terms of this. There was a second paper that kind of extended this out and showed, nope, it's still there. That was a few years ago now. And so you can kind of look at this across different processing systems. And so this sort of flattening out because of mismatch, you're like, huh, all sorts of interesting opportunities here. And I'll look at that, but it also made it very interesting as you start talking about the analog side. Like, well, okay, maybe we're actually in a pretty good shape there. And how do we start to build from this? And by the way, this is sort of core processing, not getting the rest of the memory access and so forth. But I want to talk about that too. I lost a slide there. Okay, so slide. Cool. So there is a whole conversation on top of that in terms of talking about, you know, how do you kind of make your architectures be efficient as you're putting this together? So everybody tracking so far? Okay.
So are you saying that TOPS per watt that people report, that's it's a misnomer, like it's.
Yeah, I'm very cautious with using TOPS per watt because you can do different things to get different numbers there. Yes. And it also depends if you're playing with it being adds or you're playing it with, you know, because you can say, hey, I can just do everything with just adds. Or if it adds, well, then also what's my accumulate number? What's the other? There's a couple things in the architecture you have to watch for. Whereas you say, I'm doing max, it's like this, it's a very apples to apples comparison. Being that careful, it usually does cause all sorts of interesting consternation when computer architects. It's a very fun conversation, but because they want that fluidness.
Just to be super precise, like with a Mac, we mean like for integers ABC, we mean A times B plus C.
A plus B continuously being added into register.
Right.
So there's an existing C and you keep adding to it.
Right. So
right.
It's not the full like a vector times a vector, but right, because
it's precisely the core operation. No, but the fair point, right? It's precisely the core operation to do that, right? Because if you do vector, this is exactly the operation you need. Which, by the way, this is exactly the operation that all the DSPs are tracking too. That's why we chose this, because we're like, we're going to go right with where exactly you are. And that's always been a fun thing. Yes.
Just a general question for analog. Like,
yeah,
you said you're computing in fields, whereas like for the digital it wouldn't be. Like
fields, yes. Keep going.
Like
there's a lot to that, just that little comment there, but keep going.
What is the like general range? Do you operate within like a range of error that you expect for the computation?
Yeah. So here's a simple answer. Basically, it comes down to usually you're talking about, you know, the computation itself usually is real valued, typically, if you look at it from a computing theory, usually your input and output alphabets are typically discrete, because that's usually what we can handle. But the internal engine is continuous. Typically, that's the model that we're mostly playing with. Because you can go, well, noise, but noise means I've actually got discretization, and the answer is that's not right. It turns out fundamentally there's something very different going on there. It's true here, it's true in almost every physical computing, right? Another physical computing would be quantum computing, and the same conversation comes out there. Yeah. That's a short answer, so I could spend another hour on that. And maybe you want me to, but.
Sure, yeah, thank you.
Yeah, no, exactly. So the thing that's interesting about this is that, then you start to go, well, how do all these energy efficiency things kind of work out? And you start to go, all right, well, you can start to say, I actually like putting things where the first DSPs to where that wall was hitting. And again, it shifted a little bit. You can talk about when we hit FinFETs, it got a hair better. There's one or two small jumps, but ballpark, we're not far off of there still. And the energy efficiency wall, this is a factor of 1,000, which is cool, right? But you go, wait, on just the analog itself, it's another factor of 1,000. That's huge, right? And then you go, wait a minute, but if I take an estimate where neurons are, it's another 5 orders of magnitude below that. And I will promise you that I have not given the neurons their due. I'm sure they're better in terms of equivalent computation if I did it efficiently on a digital system. And so you're like, there's a whole lot of room left here. The other thing is I usually like to talk about when I really get into neuromorphic techniques, it is, okay, get past the analog computing questions. You need to be better than that. And so that's where it always gets very interesting in the conversations is how do you get better?
But it's an unfair comparison because you also need to have ops as well, not just efficiency, power efficiency, right? Throughput as well.
This is one metric. I could do this in other orthogonal spaces.
Because I can go down to land lower limits and I can say, look, that practically I can consume.
So the argument here has always been, the way I try to put this to be careful, was to go, what is kind of the equivalent kind of, with similar levels of computational, what would be the best, most efficient way if I took it with a digital approach to compute what I'm seeing on the biological neuron side? So of what I'm seeing, and I'm thinking particularly here gets into coincidence detection and other things in the dendritic systems. So I'm pulling all that into the conversation. So there is a bounding to it. Yes, I'm not saying, being careful there, but it's still kind of very resting on a computation question. Does that make sense?
Because adiabatic, that will fall below.
Well, the adiabatic is really interesting, and depending on how it starts working, it's going to be fun. Yeah, there's some wonderful techniques for experiments. Yes, but it kind of gives you the starting point at least. And now we can start throwing stuff at it versus going, I don't know where to go. By the way, this was actually part of that whole scale that was done 13 or 11 years ago. And what is a paper that really talked about what's a neural roadmap discussion, and I can talk lots about that discussion. Basically, could you build cortex with the current technologies? So to get there, I want to start to talk about how do I get to some of these questions of I said, look, there's a vector matrix multiplier, I did all these things. How do we get there? And how do we begin to start building up from this? So I'm going to just go a little deeper into transistors. Many people here are familiar with transistors, maybe, at least PFET transistors, right? So if I were to just give you a normal PFET device and not put the other stuff over here, you'd go, this is a gate sweep. And you have your subthreshold region, which all of you would know because that's the primary operation for a FET. And then it's this, falling off above threshold, right? Y'all with me, right?
Yeah, of course.
Okay. By the way, in case you're curious, I say that a little bit tongue in cheek, but it's partially true, right? Because it turns out that the subthreshold region is what you can really count on across all process scaling nodes. And on top of it, it turns out as soon as you get to 40 nanometer and below, you're actually having velocity saturation in your channel of your diffusion currents at the upper end. What do you think your above threshold model looks like at that point? Yeah, just that point you just go, yeah, whatever, it's not linear. It's not even linear. It actually goes sublinear very quickly. It goes quadratic for a tiny region because you can always approximate linear and then just go sublinear on you. Lots of good data on this. Yeah, no, you really want to stay sub-threshold as much as you can get away with it. Not always, but use every part of the device, always good, just worth thinking about. But the thing is that all these plots these pictures would have come from a single device. And you're like, wait a minute, I would expect one curve, not 20 curves. And it turns out what I can do is simply, if you want to say in a very simple sense, I can put charge on this floating gate node. That charge basically, in one level, you could say, changes the threshold voltage. It actually affects the flat band voltage, but we'll go with that. It'll move it back and forth. But also if you're in sub-threshold, a shift horizontally means a multiplicative factor between things. Which you go, oh wait, multiplicative factor, that's useful. I can do things with that. And so, you think, wait, that works well for a VMM structure, which is exactly how you start to play that. And then you worry about, is it differentials or not? And there's all types of techniques, and multiple people in this room have talked about that in past lives. One of the first things that's important, though, is you do actually have a floating node here. And most people will go, isn't that a DRC error if you've done any layout? You're like, I should not do that. In fact, it's great fun these days as we've been doing things in small nodes. People go, hey, that's a DRC error. You're not supposed to wave anything. Like, yep, that's the point. Like, oh yeah, right, never mind. We'll let you have that one. So that turns out to be important, and then you don't put any context to it. Because typically most process time you put context on it, you lose retention. And one of the things that's important here is the actual retention of these devices. I program charge on this. And I program charge, and then I would look at it, 10 years later, and I've moved maybe 10, 100 microvolts over 10 years.
Have you checked over 10 years?
Yeah, we have actually. We've done accelerated tests. We've checked over. We actually, by accident, it turns out a couple of them, but put a chip
So
on.
go back in the cabinet, find a chip.
Yeah,
to go, and it
yeah.
works.
Actually, it was dead on where it was. So cool, right? We've been doing this long enough. We had more than 10 years to try. Yeah, it actually happened by a set of class chips that we had, and we went, hey, let's go back and look at it. It was exactly bang on where we put it. Good stuff, right? Also accelerated lifetime you can actually hit the temperature way high and actually do accelerated temperature concepts. Works really well. And there's all sorts of comments about like, how good is it? Hey, David. And so that turns out to be kind of fun. But definitely I can say that's fairly good across a number of different things. We will program these up to single electron accuracies typically, at least a couple. We don't usually get to single. There might be some fun at single, but fair enough. So we definitely can, very common for us to be even on chip doing 14-bit accuracy. I can explain what we do for those who want to get deep into it. Just know we can get really good accuracy on these structures. And there's nothing particularly crazy about it. It's like, well, here it's a MOSFET in a process. For those of you who can read cartoons and planar CMOS. That's a transistor or PFET. A little magic-y, but sure good enough. And then the entire questions on the design are all about the capacitors. What capacitors do you have to your gate material? Usually that'd be polysilicon, but not always. What capacitors do you have to your gate material without making contact? That's the fundamental question you ask. And also nice to have one that you can actually play with the tunneling, that you can also do high electron injection for programming, but finding capacitors and finding the behavior of capacitors, because the funny thing here is capacitors are DC elements. Virtually DC elements to your perspective. Yes, over the gauge of the universe it'll go. But within the lifetime of the chip, they're DC elements. And so you see a lot of effects straight up and that are really nice there. There's some other things you got to pay attention to. But yeah, there's different capacitors. So like you're on a 130 process, for example, you have reactor caps, you could have like some overlap caps, you can do some other caps. We do all sorts of crazy stuff. And most of the artistry is in the caps. Or actually, how do you put this together? It kind of makes sense?
Yeah, just one question. I mean, you don't have an initial condition, like you don't know where you're starting from, right? They're starting this from.
When it comes back, who knows? In theory, who knows? It turns out actually in practice, because there's some high temperature behavior in the process fabs, they actually come pretty close to each other. But then when they come back, the point is then how do I then put charge on it? Because if I put charge on it and it stays there forever, I've got to have another way to get to it, right? And that's where we talk about doing things like hot electron injection, electron tunneling. There is exquisite sort of precision on the hot electron injection you can build in crossbars. So you can actually program one device and only one device out of the entire array beautifully. So selectivity is not a problem. By the way, the number of writes isn't a problem either. Bunch of, because we're very careful in the insulators we pick. And so therefore, I get trillions of writes out of these things. And I can be very careful about it. And actually the original technique we used to do that became the technique that many people use for their embedded flash cells now. Across the industry. So like, yep, most of them don't understand it, but they use it, so good enough. That's where that begins. So
how do you simulate them? Or is there a special tools that you need to simulate this stuff? Or?
right. So most of the time when we build these structures, we're going to program them. Effectively, we'll program it and then run stuff for a while, right? So the programming infrastructure, we learn how to do that and not worry about it too much, right? So then the question is, well, how do I then simulate something that's been programmed with a certain amount of charge? And the trick we always use, and I can go into this, it's great to tell people want to do this, is we just put a gigantic resistor here, 10 to the 22nd ohms. Because why? Because it gets you somewhere in the neighborhood of well, actually 26 would be close to the leakage number. People go, but my simulator doesn't let me have that tolerance. Too bad, just move it. It's fine. It turns out that the numerics of the simulator are actually quite happy with you to do it that way. And so then the reason we do that, and we do it, there's a bunch of different ways people talked about it, but that way works really well because the way I set it up there sets my DC conditions. And then everything in the transient part of the simulation is exactly how you would see it in the measurement, including the jumps and everything, and capacitive jumps, everything. So it's just perfect. So that's the technique that my group's used for 25 years. Works great. Everything else has its flaws that I've seen to date. Maybe somebody will correct me on that. Nobody's jumping on the edge, so we're good. Cool. Questions, by the way, more questions are good. Because I can just up here and ramble for a while, but so the thing that comes out, so the thing is we start talking about this in the target floating gate element. There's lots of different discussion, lots of people started playing with these and talking about it as standard CMOS. There's interesting stuff. Yeah, so including one colleague of mine ended up having at Georgia Tech, which was great fun once I got there. And so people looked at some things, have been working with, and there's ideas around it. We can talk through that, but I think that the definitive thing really hit when we finally said, hey, look, I can actually do something that was called single transistor learning synapse. Maybe a little bit broad at the time, but it actually just kind of worked out. Because we looked at the structure and said, all right, I can not only get good curves, I can also program it, I can get non-volatile behavior. It's small sizes, one transistor and a cap, maybe only two if we're doing certain differential things, fine. And I can also get really low power out of this, and I get the signal adaptation. The low power part needs to not be ignored, because I can get some threshold currents down to 10 picoamps, 1 picoamp. Works great, no problem. And that was huge in terms of, because others cases you don't get that. This actually became the starting point. We started getting the first sort of single crossbars. This was all in standard CMOS. And this has worked in CMOS processes from 2 micron CMOS, CMOS, 2 micron, 350, 500, 350. I can go down the list: 130, 65, 40, 28. Can I pinfest them? We're good, right? It just works as you work your way down. And that was actually being very, very careful. And it was actually related to something Carver always talked about, which was make sure that if you're going to do analog systems, if you're going to do this for real, for a computing space, it better be able to scale with the process nodes. Because if you can't get there, you're eventually just going to be left behind.
So you said that it works in a range of 10 picoampere to 1 picoampere.
Oh, you can get much higher. You can go up to 100.
What is the range of the leakage current?
So like what the dark currents of the transistors are? Yeah, so the dark currents of the transistors typically depend, and that's still process dependent. But if you were to talk about, say, 130 nanometer process, you're typically talking about femtoamps, 100 femtoamps, maybe it's the dark current. So you can drive yourself all the way down there.
You can also get rid of that, reduce that. So Bernabe has a nice technique.
Yes. There's some interesting techniques when you get down there, and yes, there's good people, good thing. But if I just take just even a normal PN junction, kind of the number of the dark current, it's gonna be around that range. And we actually have IV curves that will, and things, circuits that actually effectively you can see all the way down.
So Jim, one question I had, you said that the process scaling.
Yeah.
So what, like 65 nanometer or so?
Yeah.
Do you use the thick oxide or the normal transistor?
We always use the thick insulators.
Okay, so that.
They do scale. They don't scale quite as aggressive, and that's unfortunate. Usually. Yeah, that's a fun question because they are a little bit, the transistors are a little larger as a result. The retention's perfect, so everything is good. And by the way, that size does decrease with process node. I can say that with definitiveness. The issue that you run into though is you go, well, all right. So you know, I guess you have to figure it out now. Could you actually make that transistor smaller? Because they're actually being optimized for 5 or 6 things, and I only need one of those. We need insulator thickness. And the answer is you absolutely could. There's a lot in terms of transistor physics. The issue is that if I'm doing an MPW run, they're only going to, they usually say, here's what your mass levels are. You can only go so far. MPW means you're doing multi-project, so multiple things on the chip. On the other hand, if you say, here's my wafer, I'm just gonna buy the whole wafer, thank you. You can do whatever you want because they have your cash. And off you go. So there's different things you do once you get to that stage. And there are some things you can do to tighten it up. But it does require understanding the process and understanding things that often are not characterized in the process when you get your PDK from the process node, then you sign your NDAs and all the happiness that we've all heard about. There are things you actually usually want to dig into a little more and go, hey, can I do this? Can I do this? What's this cap value? What's this value? What's this value? That's usually where the stuff gets interesting. And by the way, almost all that's true, and everyone in the commercial industry, all of those are trade secrets. No one will tell you how they built it. No one will actually even put it in a patent. Because if you put it in a patent, you told everybody now they can pretty much tweak it and get around you. So you don't ever do that. So there's no, it's kind of funny, there's actually very little to worry about in this space from an IP perspective. A legal IP perspective.
So if that's done on CMOS, I guess that's something that you require a specific PDK for, or is that something you can build by yourself somehow? So
You can build by yourself. Yeah, I mean, everything I've talked about, you can do by yourself right now. Of course, you could also read some stuff we wrote, and of course, I could also share like, hey, let's do this in the process, and let's do it. And by the way, because I don't, you won't have to sign any NDAs if people want to like see what the devices look like on the 130 nanometer process. I'll happily show you what we got on Skywater. Because that we can just tell you openly. And I can show you what we did, and I can then give you roughly what we do for other things. For people here, people virtually, you can talk to them.
Something in my practice, I mean, we didn't discuss this, but we were planning to do something potentially with defense, right? So if we put F structures there, it might be interesting to do them side by side and just.
I think that's awesome. I'm up for it. As long as anyone who's guiding that process doesn't kill me. You're suggesting great.
So Jim, do you know like how, like for some of these gauge all around processing, you still would have to use a thick transistor, right?
Yeah. So if you're using a FinFET process or get all around, you're still using a thicker insulator, yes. And every process has at least one, if not more. So yeah, if I was going to do a 5 nanometer design, that's what I would use. For example. Yeah. No one's writing a check for 5 nanometer yet, but if anyone wishes to, we'll do it. Yeah, definitely. But yeah, so basically this turns out very quickly to basically be, and if you look at it closely, basically just an array of transistors. Sometimes we'll balance them, 2 of them to get some differential things. Sometimes we'll be able to balance things off on the edges and so forth. For those who, there's some really interesting work there, been done by different people on that. In fact, one really nice paper, that we have to dust off that Gert did once upon a time on some stuff, doing differential stuff. So very, very good stuff. Very good things as you look at it. And so all these things are in play. But I will say that the subthreshold part is extremely important because you have so many of these devices, you want to get the power down. And that's one of the big issues. And also when people have tried to do metrics of things, they've always kind of like closed their eyes and went, yeah, I don't want to talk about this. Like if you look at all the metrics in DARPA Synapse, that's quite clear. DARPA Synapse was actually adapted these things and ignored the power conversation the way it should have been done. for some very interesting reasons for those who care about it. But as far as we can, I think it's fair to say this was definitely the first very solid single device crossbar. But there are people who did some early stuff before that, so I'm also gonna be careful with that. But there's some really neat stuff in all of this. And again, works across processes quite well. So a device, yes, crossbar. The next thing you go is, well, how does that work exactly? And so maybe it's already obvious to everybody. Is it already obvious how this works? No, a couple of you guys. So a couple of you can look at what's over here on the side here, is that each of these transistors, right, there's a floating gate in here, and that effectively is you want to say almost sort of programs a transconductance of a sort. And so if you think about it, it's a transconductance and times the gate voltage coming in there if you linearize it. For those of you who are going careful, it's like, yeah, there's some nonlinear terms. Yes, put that aside for a moment. We can get to all of those questions. It is also nice with capacitors. You can linearize things. We'll let all that sit for the moment. But you can actually talk about, hey, normalize it to a baseline transconductance, whatever that weight is at 1,1 times the input. And then the cool part, so you can do this. Now, do understand I'm talking about this as current sources, not resistors. That's actually better from an SML and a signal perspective. So you could actually turn these all into resistors, but you're going to not do as well. And I think that's true for most kind of technologies of this form. But that's where we would start with that. And then once you have current, right, the cool part is that each of these have a current coming out onto a single line. They all get summed together. Yay. That sum is Kirchhoff's current law. It is the current of the summing along the line is perfect. It is a really nice thing that it is in fact very perfect. And so that is a perfect summation you get there. And then of course you got to figure out what do you do on the back end of it? Cascoded, you still got to figure out what you're going to do with the currents. Fair enough, certain design question at that point. But within this structure, this is how this would look. And this gives you a very nice sort of vector matrix multiplication. Because now it's basically, I get something for the sum of this. Of course, in vector notation, it's matrix and vector. And it starts to go, wait, this looks like real math. This is fun. Yes, there's something to what you build on the back side of this, and you have to think about that. But on the other hand, this works out well. The other thing, if you look at this, is this being this one big crossbar, that also feels like this one big memory. So that's kind of cool. And you're like, huh, so wait a minute, I'm actually putting a vector in, getting vector out, going through a whole memory block. That's cool. It feels like I'm computing in the memory. Oh yeah, I am. And this is, I think things that we started, people played with a little bit beforehand, but the definitive discussion on this, and this is a picture from that original discussion in 2001, was the conversation of digitally. And again, this gets into architecture, right? You might have a processor and have a Mac, something that does multiply accumulate. You're like, yay, this is great. And so that might be at some number per MMAC, say a quarter of a milliwatt per MMAC, if you're running it continuously. But getting the data just to feed this processor is significantly higher than that, even if that processor and the memory are right next to each other. You just wire bond across. And so that's where this kind of number estimates came from. And you're like, huh, versus saying, hey, I take the whole, say, signal input into that crossbar, and basically what it takes for the complexity, reading a couple rows out of here, I'm already done. And so the beauty of this is saying, look, I can, by basically kind of computing through where the memory is, there's a lot of efficiency. This is a mesh architecture. People had understood what a mesh architecture was and the efficiencies of it. Even, we talked about in the analog space, well, a decade before this, but you begin to start to see the pieces come together in a nice architectural framework.
Just want to make sure, because it looks very similar, like deceptively similar to how people build like resistor RAM crossbars, but this works by a different principle in some way, right? Because here, it's not like that you're using the transistor like a resistor where you have like a gate voltage set somewhere and then the transistor acts like a resistor and you have current flowing through that, but instead it's like the input is modulating the gate voltage, the transistor acts as a current source, and then you sum up the currents that are generated here.
Yeah, that's right.
It's a little bit different.
It's a little bit different. It still is very similar. I mean, I'm not going to say that they're very similar thing, right? And you could argue that it's a case of I've got a crossbar devices, and I say, well, how do I optimize the device that I'm using? But yeah, and in fact, you actually could run these as resistors.
Yeah.
we've looked, we've actually done that before, and it's okay. There are times we'll actually want to, instead of run off the gate side, run off the source side. But I will tell you, even when we run off the source side, we're pulling as current sources, not as resistors, because the dynamic range you get is much better out of the circuits. So it's a very circuit detail question, but that's very much where that would come from.
So you get some linearity here though, right? This is
Yeah.
not,
I mean, yes, you do, to start with, yeah. And there is always some fun exponentials that are lurking in it.
the rate of doing a translinear.
You can do this as a translinear circuit, and yes, well put. Because you could actually say, let me take stuff on the edges. And this is one of the other things that we understood pretty early on was, hey, if I put stuff at the edges, that's order, that's not the order n squared that I need for, say, a full wave matrix, right? So we did do things at times and say, hey, let's do current inputs in here and do a translinear thing. And that actually works very nicely in some applications. In some applications, it actually didn't buy you as much as you thought it did. But you can play out, you can do things to stretch the linearity. The other place you can stretch the linearity is just the fact that this capacitive input, if it's a gate coupled input, definitely allow, there's already a capacitive divider here. And that capacitive divider actually opens up the linearity of the structure, as well as anything else would open up the linearity. In fact, it's a noiseless way of improving the linearity. Anytime you open linearity, you do change things on an SNR basis, but this is always the trade-off people play, or noise basis. I mean, you can win with it, which is what people do all the time.
So that helps with the linearity with voltage variation. What about with temperature?
Yes.
So the minute you start talking about, temperature is great. So the minute you start talking about, because we spent a lot of time asking these questions, we want our stuff to be stable. And so temperature is fun because if you do temperature, I mean, certainly if you can do things like some of the translinear stuff, it helps. In general, we always try to make sure that when we're doing this for like careful temperature things, we actually will kind of balance these capacitors built off of some sort of floating gate reference circuit that actually will actually lock this down so all the voltages are not shifting too much from each other.
Yeah.
And so the temperature, and so then I can have very nice still programmable weights, but I still can keep things within 8-10 bit precision even differentially, over 0 to 60 C or something range.
So how do you create such a stable capacitor? Because even that reference capacitor, what is it, KT over C?
Oh yeah, there's always noise in the system, so you treat mismatch and noise separately and those discussions separately.
Okay. Yeah.
And you track through where those are, you have to. But if you do that, it works out. And it turns out there's a whole set of good analog circuits, which I didn't really bring all the slides for, but I have them and I can show more about what happens when you do like really good floating gate reference circuits. In fact, some of the more interesting reference circuits that people have proposed since then, actually, since we did the first couple ones, are actually things that you actually find in industrial products that not the floating gates, but people use different threshold voltages to play off this stuff.
Is there anything stopping you from using the band gap?
Yeah, we can use a band gap. Of course, it turns out there's like a core thing is a basically a bootstrap current source, right? It's part of the band gap. It turns out there's a floating gate version of bootstrap current source, which is really nice. It's not only there, but it's also programmable. So right, and very temperature insensitive. So there's a whole bunch. So yes, so I can go down that rabbit hole temperature if you want, because it is a super important question to ask. And I'm going to get into specialists really quickly.
Program GM to be temperature because you have that knob.
Yes, you can. Yeah, you can play games on what is the transconductance if you play it that way. There's actually a bunch of interesting. Actually, one of the things we've loved about the floating gate stuff is it actually made us ask all these temperature questions first order. And so we actually said, well, let's actually look at the temperature effect on just basic circuits first order. And because people don't do design for temperature, except for Bernabe. Yannis Savidis is one of the best, the one analysis as a PhD student. That's what everybody copies. Other than that, there was all, up to 10 years ago, there was nothing. We looked hard. Everyone just does 20 spice sims and hopes you get it.
Shanti, what did you say about GM?
There's the GM question that people will play with.
You can program the GM to be temperature insensitive because everything else is on this side. It doesn't.
As an after the fact.
They're
change.
You have to.
Keep dynamically up.
Yeah, there's an interesting spot for GM, and I just as people are talking about, yeah, there's some neat stuff, but I'll leave that. Yeah, it's a fun technique, but yes. But it made us ask these questions, and then it made us rethink circuit design. And it's actually changed the way I teach circuits, even my for like senior level circuits at Tech and stuff, because of this.
I have to ask one very dumb question. This is kind of the data path, and for programming, like, do you need any additional wiring here, or do you use the wires you have here, like for the organic?
Depends heavily on the circuit that I'm building. So if I'm building just a straight crossbar structure, it's usually pretty easy, and I can build the programming infrastructure on the outside edges. But we build a lot of heterogeneous stuff where we build into many different circuits, and then you got to think a little harder of how do you pull the program, how do you do stuff in programming mode versus run mode. And yeah, there's a detailed conversation there, but it's still pretty efficient. But there's certain things we'll go, we'll use this technique, we'll use this technique, we'll do this thing.
So we're not hiding twice the complexity in the programming?
Not at this level, no. There's a few circuits I probably could be, but not here.
Down the road of programming, are we using like something Val and what IMS, or is it capacitive division?
Capacity division wouldn't do it.
Really?
No, because it only just that's just you're moving stuff around. Valor no time tunneling is the erasure mechanism we use. Hot electron injection is the programming mechanism. And that's huge because it allows the key with hot electron injection, subthreshold and near threshold, to where we use PFETs because they'll do it nicely, is that you actually have a product of field and current. Exponential field and current, and so you get a really beautiful ability to hit one element in a crossbar, measure that element in a crossbar, or program that element in a crossbar without any interference with the rest, which is why I get single precision, electron precision out of this stuff. Because pure Valor non tunneling always has some coupling, particularly depending on, unless they put a tunneling junction in every element with or a tunneling amplet, that's usually.
So which voltages do you need?
Yeah,
what is that?
I'm sure it's changed over the years, but what voltages are we talking?
Depends on the process nodes. I would say on the typical process node, what do I want to pick? I could pick a lot of nodes. I should just have a table and just here's how they all shape and why. Let's say I just pick 65 nanometer CMOS. I think the tunneling voltages we've been using have been about 8 volts. Programming usually is the supplies for about 5.5. 5.5 the issue. 4.5 is fine, 5 faster, 5.5 is even faster. I don't want to wait that long cycle.
So you have the separate power supply for programming? And
we build all that infrastructure and yeah.
Okay.
Yeah, and by the way, it turns out to be no problem. People go, but you're putting 8 volts on that process, everything must die. And I'm like, no. You just got to be very careful. You got to be a little bit careful where you're routing your lines, but the point is the first thing that's likely going to affect you is the power Northam tunneling of that cap. So that's the first thing to go, which is the thing I'm trying to get. So it's fine.
So if you want to go that once to electron precision, you have to drop your voltage probably.
Not always, no. Well, yes and no. It depends on voltage and time. So there's a product of those things. And we use both. Yeah. So this is where its crossbar starts. I've lost track of time. Am I down to 5 minutes? No.
Shit, I don't know.
How much time I got?
Probably around 10 minutes. That's
So this is great. We're having a great time. Part 2 no, we could do part 2 and 3. It sounds like this is awesome. I love the question. So I'll go where I can. I'll give you 1 or 2 bits at the end just so you kind of know where the heck this might be going. But yeah, so it was these kind of things that got us to the Higgs hypothesis on that. The one thing I will be very clear, and I'll just kind of hit this briefly on the structure, is that this actually, the implication of moving data is so important because, the computing is really inexpensive, right? Which then, cool, the computing goes down to a factor of 1,000, so then the cost is moving the data. And so communications where you pay. And I know Andreas talks about this a lot, rightfully so. And I agree with him strongly on that. There's the conversation that's come out from multiple people that say that basically just assume that when doing analog architectures that the computing is free once you get it set up right, and everything is the data communication. And so this is one of those things like, hey, if I'm building a nice network, this is great. Keep everything local, keep all the data going through. This actually came off the roadmap paper discussion. If you just say, hey, let me take all these events and run them to a processor and push them back, that will probably cost you more than the computing itself. You have to be very aware of these trade-offs. And then if you start to say, hey, cool, I'm just gonna kind of reload my memory constantly, which lots of people like to do, particularly that time frame. That will, kick your cost by a factor maybe 100 or more very quickly. The architecture questions are essential here, and understand what you're dealing with very efficient computing. By the way, the minute you start getting into more neuromorphic kinds of things, properly done, very efficient computing memory, that computing gets even more efficient if you do it right. So guess what? This is even more a problem, not less. So something you definitely always want to watch for. So one of the things then is there's really good theoretical modeling and all of this now to kind of look at the kind of numbers and speeds. These are actually numbers that came off of, I think, estimation on a 28 nanometer process node. So yes, there's some nice numbers. And that also leads to a whole bunch of other interesting computing questions, which then gets you into things like you can actually start running this sort of adaptive filter structure of a couple different forms. It's one of the early ones. Gosh, it's 20 years ago now. And one of the things that you can do is basically turn on the high electron injection, and the tunneling. You get a balance out of it. And it actually will find, you can actually do the adaptation while you're running the data through. Kind of crazy, kind of fun, but it's actually kind of some things you're looking for there. You can do a whole bunch of other interesting computing examples, but then you can also get these things that are called FPAAs, and I would be remiss if I didn't really see something about this before I left, which you go, field programmable analog arrays. Well, what would one of those look like? That. Wait, it's the same laptop and this board, actually. By the way, this is what I carry on with me. I carry a lab with me mostly. Analog discovery stuff, all there. So this turns out to be a lot of fun, and this is actually what the structure looks like. I'll show you what that measurement is in a moment if you're curious. But yeah, so if you're talking about how many people are familiar with FPGAs? Cool. So this makes sense to you, yes? Yes. And some of the history, and it's really just wonderful stuff. Cool. So when I get a little further to this is probably where it gets a little less familiar. Some of you may know. One of the beautiful things is that there's a whole architecture that's called a Manhattan architecture. It's very much like what you'd expect if you were in the city of Manhattan. Buildings, which are your basically computational blocks, computational logic blocks, streets, and intersections. In fact, I still remember walking with a friend of mine down Manhattan, and was very surprised when I made kind of a joke, hey, we could do this, we do this, just like what you do on normal. And he was like, one of the early FPGA people was like, oh yeah, that didn't even dawn on me. I'm like, okay, we're walking through, I'm like, it's exactly what the architecture is. It's really a very useful thing, but the whole point of why this actually is what really saved FPGAs, saved their bacon, how they handled the routing, is because digital routing is local and sparse, right? So if you take any sort of digital structure and you target it on something that's local and sparse. And so you want something that actually handles local and sparse. And it turns out the Manhattan infrastructure does a beautiful job with this. Take the slight side point, you go, wait a minute. Neurons are often local and sparse too, aren't they? Right. And there's a whole discussions around that perspective, or wait, I want to do a whole bunch of, want to do a Hopfield network. That's a bunch of local and sparse things. Right. This is the way that you go, wait, I'm not just doing one crossbar, but there's a very clever way of handling this. And the FPGA people kind of started with this, and we just said, hey, let's just build on this. There's usually an understanding that in FPGAs you lose something because of the configurability, fair enough. Those are pretty typical numbers. But then as soon as you get in the end location, you're like, cool, I can do something similar. Sort of same routing structure, will kind of go there, similar place and route infrastructure, you're like, wait, analog place, what? Right, and then there's a whole abstraction side of this that you try to abstract this from the mixed signal side of this. But basically, an FPGA basically is just like an FPGA, but now I've got analog elements in here too. And that's kind of where this is all going. And so when I talk about an FPAA, that's what we're looking at, it has these pieces.